Welcome. Friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deepest mystery of space itself, the ancient whisper that fills every corner of our universe. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you in this moment. As breath settles and thoughts begin to drift, the universe speaks in frequencies older than galaxies. A whisper fills the darkness between stars, so faint that it requires the most sensitive instruments ever built just to detect its presence. This is the cosmic microwave background radiation, the afterglow of creation itself, streaming through space at nearly 3 degrees above absolute zero. It arrives continuously, invisibly, carrying within its static the deepest secrets of existence. The radiation emerges from every direction simultaneously, a bath of ancient photons that have been traveling for 13.8 billion years without pause. These particles of light began their journey when the universe was only 380,000 years old, a mere infant by cosmic standards, when space itself first became transparent and light could move freely through the vastness. Before this moment, the universe existed in a state of complete opacity, dense with free electrons that scattered photons like morning mist scatters sunlight through a forest canopy. Scientists call this transition recombination, though the term misleads. Nothing was actually recombining. Instead, for the first time in cosmic history, electrons were settling into stable orbits around atomic nuclei, creating the first neutral hydrogen atoms. The universe had cooled sufficiently from its initial fireball state that these fundamental particles could finally bind together without immediately being torn apart by the ambient heat. With electrons no longer free to interfere with passing light, photons suddenly had a clear path through space. The universe, in essence, opened its eyes and began to glow with a soft, pervasive radiance. What emerges from this primordial moment carries information encoded in temperature variations so subtle they measure in millionths of a degree. Fluctuations so tiny that detecting them requires cooling instruments to within a fraction of absolute zero. Colder than the space between galaxies. Yet within these microscopic temperature differences lies the blueprint for everything that would follow over the next 13 billion years. The first stars igniting in primordial darkness, galaxies spinning into existence, and eventually planets where conscious beings would develop the technology to hear this ancient cosmic song. The pattern speaks of a universe that was almost perfectly smooth at its moment of transparency, save for tiny ripples that represented the seeds of all future structure. These fluctuations, initially no more significant than the quantum foam that underlies reality itself, would grow over cosmic time through the patient work of gravity. Dense regions would attract more matter, becoming denser still, while sparse regions would empty further, creating the cosmic web of filaments and voids that astronomers map today. Radio telescopes across Earth continuously receive this signal. Massive dishes pointed toward different patches of sky, each one a technological ear pressed against the cosmos. The radiation arrives as a cosmic broadcast that predates the formation of our solar system by nearly 10 billion years, older than the oldest rocks on Earth, older than life itself. The photons detected now left their source when the universe was 1,000 times smaller and 1 billion times denser than it appears today, when the entire observable cosmos could have fit within the orbit of Neptune. These ancient messengers have witnessed the birth of the first stars, massive blue giants that lived fast and died young, enriching space with heavy elements forged in their nuclear hearts. They have traveled through the formation of the earliest galaxies, watched as supermassive black holes grew at galactic centers, and observed the slow expansion that continues to stretch space itself, cooling their energy from the blazing heat of creation to the whisper-cold temperature they carry today. Within this seemingly random cosmic noise, researchers detect patterns that challenge the fundamental assumption of cosmic uniformity, the cosmological principle that suggests the universe should appear the same in all directions when viewed on the largest scales. Certain regions appear slightly warmer or cooler than statistical models predict, creating alignments that some astronomers have provocatively dubbed the axis of evil. The name reflects not malevolence, but scientific discomfort with data that refuses to conform to theoretical expectations. The search for hidden patterns continues in laboratories where supercomputers work through the night, analyzing maps of the sky with unprecedented precision. Each new survey mission reveals finer details in the radiation structure, yet paradoxically also uncovers deeper mysteries. Some temperature fluctuations align in ways that seem to violate the cherished principle of cosmic democracy, suggesting the universe might possess preferred directions or asymmetries that existing theories struggle to explain. Modern instruments have mapped this radiation across the entire sky with exquisite sensitivity, creating portraits of the universe as it appeared when it was less than 1% of its current age. These maps reveal a cosmos marked by subtle modeling, like the surface of a pond disturbed by gentle breezes. The lighter and darker regions correspond to areas that were slightly warmer or cooler at the moment of last scattering. Temperature differences that would eventually determine where galaxies would form and where vast empty spaces would remain. Perhaps most remarkably, the cosmic microwave background represents the most perfect blackbody radiation ever observed, a nearly ideal thermal spectrum that speaks to the universe's initial state of thermal equilibrium. This perfection itself poses questions. How did regions of space that have never been in causal contact with each other maintain such uniform temperature? The answer may lie in cosmic inflation, a period of exponential expansion that occurred in the universe's first fraction of a second, stretching quantum fluctuations to cosmic scales, as consciousness settles into the rhythm of rest. These ancient photons continue their endless journey. They pass through sleeping bodies and dreaming minds without interaction, ghostly messengers from a time before stars, before planets, before the chemistry of life itself had begun. They carry within their subtle variations the signatures of physics beyond the standard model, hints of gravitational waves from the universe's birth, and possibly evidence of other universes beyond our own cosmic horizon. The cosmic microwave background radiation streams through this moment, through every moment, a constant reminder that we exist within the afterglow of creation itself. In its patient whisper lies encoded the entire history of a cosmic evolution, written in a language of temperature and polarization that humanity has only recently learned to read. And still, after decades of study, it keeps its deepest secrets, suggesting that the universe contains patterns and purposes that may forever dance just beyond the edge of understanding. The temperature of the cosmic microwave background holds steady at 2.725 Kelvin above absolute zero, a measurement so precise that it represents one of the most accurately known quantities in all of cosmology. This number emerges from decades of careful observation, refined through successive generations of increasingly sensitive instruments until scientists can specify the cosmic temperature to within a few thousandths of a degree. The precision itself tells a story of a universe whose thermal signature has remained remarkably consistent across 13 billion years of expansion, cooling with mathematical predictability as space itself stretches toward infinity. This frigid whisper carries the thermal memory of a universe that was once blazing hot, compressed into a state where matter and energy existed in perfect equilibrium at temperatures exceeding 10 billion degrees. The photons detected today have cooled through cosmic epochs. Their wavelengths stretch from the visible light spectrum into microwaves by the relentless expansion of space-time. What began as radiation hot enough to disintegrate atomic nuclei now arrives as the gentlest possible electromagnetic caress, barely above the theoretical minimum temperature where all molecular motion ceases. At the moment, these photons began their journey. The universe glowed with the warm orange light of a dying campfire. Roughly 3,000 Kelvin, hot enough to keep electrons dancing freely around atomic nuclei, unable to settle into stable orbits. The cosmos existed as a vast plasma, opaque to light because free electrons scattered photons in every direction, like fog scatters headlights on a country road. As space expanded, this radiation cooled in perfect accordance with the laws of thermodynamics, its temperature dropping in inverse proportion to the scale factor of the universe itself. The mathematical relationship holds with elegant simplicity. As the cosmos doubles in size, the background temperature drops by precisely half. This cosmic thermostat operates according to the fundamental principle that expansion work cools gas, whether in a car engine or in the universe itself. The process unfolds with the inevitability of physics, each photon losing energy as the wavelengths stretch across ever greater distances, cooling from the brilliant white heat of stellar interiors to the whisper-cold radiation that now fills intergalactic space. Radio astronomers first detected this relic heat in 1965, quite by accident, as a persistent noise that interfered with sensitive communications equipment at Bell Laboratories in Holmdel, New Jersey. Arno Penzias and Robert Wilson initially attributed the mysterious signal to terrestrial interference, perhaps radar installations, radio broadcasts, or even the droppings of pigeons that had taken up residence in their horn-shaped antenna. They spent months systematically eliminating possible sources of contamination, cleaning equipment, removing birds, and recalibrating instruments, only to find that the signal persisted with stubborn consistency. The noise appeared identical regardless of which direction they pointed their antenna, arriving with the same intensity from every patch of sky. This isotropy puzzled the researchers until theoretical cosmologists at nearby Princeton University realized they had inadvertently detected the afterglow of creation itself, the cooled remnant of the Big Bang's primordial fireball. The discovery would eventually earn Penzias and Wilson the Nobel Prize and provide the most compelling evidence for the Big Bang theory, transforming cosmology from philosophical speculation into precision observational science. The uniformity of this temperature across the sky reveals something profound about the early universe's causal structure. Measurements from opposite hemispheres of the cosmos show temperature differences of less than 1 part in 100,000, a homogeneity so perfect that it initially challenged theoretical understanding. How could regions of space separated by distances greater than light could have traveled in the universe's lifetime maintain such identical temperatures? The puzzle became known as the horizon problem. Distant regions that have never been in causal contact somehow share the same thermal history. The resolution came through the theory of cosmic inflation, proposing that the universe underwent a brief period of exponential expansion during its first 10 circumflex 32 seconds of existence. This inflationary epoch stretched a tiny, causally connected region to cosmic proportions, explaining why the microwave background appears so uniform across vast distances. What we observe today as the entire visible universe was once smaller than a proton, existing in thermal equilibrium before inflation expanded it beyond the cosmic horizon. Modern satellite missions have mapped this temperature field with extraordinary precision, creating detailed portraits of the cosmos as it appeared 380,000 years after the Big Bang. The Cosmic Background Explorer satellite, launched in 1989, first detected the subtle temperature variations that encode the seeds of cosmic structure. The Wilkinson Microwave Anisotropy Probe, operational from 2001 to 2010, refined these measurements with unprecedented accuracy. The European Space Agency's Planck satellite, the most sophisticated cosmic microwave background observatory ever built, operated from 2009 to 2013, creating maps so detailed they reveal structures across a range of angular scales from degrees to arcminutes. These maps show temperature variations that measure in microkelvin, millionths of a degree difference spread across patches of sky ranging from the size of the full moon to regions smaller than a pinhead held at arm's length. The instruments required to detect such subtle fluctuations must be cooled to temperatures approaching absolute zero, colder than the cosmic microwave background itself, and shielded from every possible source of terrestrial radio interference. The technology represents some of humanity's most sophisticated engineering achievements, requiring superconducting detectors, cryogenic cooling systems, and data processing capabilities that strain the limits of current computing power. The cosmic temperature exhibits a slight dipole pattern, appearing roughly 3.4 millikelvin warmer in the constellation Leo and correspondingly cooler in the opposite direction toward Aquarius. This asymmetry reflects our solar system's motion through the cosmic reference frame at approximately 370 kilometers per second, creating a Doppler shift that blue shifts radiation from our direction of motion and red shifts radiation from behind us. Subtracting this kinematic dipole reveals the true cosmological signal, the primordial temperature fluctuations that would grow into galaxies and clusters over billions of years. Beneath this dipole signature lies a more complex tapestry of temperature variations that serve as fossils of the early universe's density field. Regions that appear slightly warmer in the microwave background correspond to areas where matter was marginally denser 380,000 years after the Big Bang. These overdense regions possess stronger gravitational fields that caused photons to lose energy as they climbed out of potential wells, cooling them relative to the cosmic average. Conversely, underdense regions appear slightly warmer because photons gained energy falling into gravitational wells before escaping to reach our detectors. The background radiation spectrum follows a nearly perfect Planck distribution, the mathematical description of thermal radiation emitted by an ideal black body in thermal equilibrium. This spectral perfection indicates that matter and radiation maintain constant interaction in the early universe through Thomson scattering, with free electrons efficiently thermalizing the photon field. The slight deviations from a perfect black body spectrum, measured at the level of parts per million, provide evidence for physical processes that occurred both before and after the epoch of recombination. Distortions in the spectrum carry information about the reionization of intergalactic hydrogen billions of years after recombination, when the first stars began to shine and their ultraviolet radiation re-ionized the neutral gas that filled space. Additional spectral features may preserve signatures of exotic physics from the universe's earliest moments, perhaps evidence of cosmic strings, primordial black holes, or phase transitions in quantum fields that operated during the inflationary epoch. The cosmic microwave background represents the observable universe's thermal bath, a sea of photons that fills every cubic centimeter of space with approximately 400 particles of ancient light. These photons rarely interact with ordinary matter in the present epoch because their energy falls far below the ionization thresholds of atoms and molecules, yet they constitute the most abundant form of electromagnetic radiation in the universe, outnumbering photons from all the stars that have ever shone by factors of billions. Laboratory experiments attempt to recreate the conditions present when this radiation decoupled from matter, using particle accelerators and plasma physics facilities to understand the behavior of hydrogen and helium at temperatures of several thousand Kelvin. These investigations reveal the delicate balance required for recombination to occur, as the universe cooled below hydrogen's ionization threshold of 13.6 electron volts. Electrons began binding to protons, but the process proceeded gradually rather than instantaneously due to the finite probability of radiative capture. The cosmic microwave background thus emerged not from a single moment, but from a period lasting roughly 100,000 years, during which the universe transitioned from complete opacity to nearly perfect transparency. This recombination epoch unfolded like a slow fade rather than an abrupt switch, with the last scattering surface possessing a finite thickness that slightly blurs the temperature fluctuations we observe today. The duration of recombination places fundamental limits on the resolution with which we can probe the early universe's structure. Current ground-based telescopes contribute complementary measurements of the cosmic temperature across different frequency bands and angular scales. Observatories positioned at high-altitude sites like the Atacama Desert in Chile and the South Pole take advantage of thin, dry atmospheres that minimize water vapor absorption. The South Pole Telescope and the Atacama Cosmology Telescope focus on small angular scales where the primordial signal competes with foreground contamination from our own galaxy's dust and synchrotron emission. The temperature of this relic radiation continues to decrease as the universe expands, following a predictable trajectory toward absolute zero according to the relationship T equals sine tiro, 1 plus z, where z represents cosmological redshift and tiro denotes the present-day temperature. In the far future, when stars have exhausted their nuclear fuel and galaxies have dispersed through cosmic expansion, the microwave background will have redshifted into radio frequencies, becoming progressively fainter and colder with each passing eon. Eventually, after trillions of years, the cosmic microwave background will fade below any conceivable detection threshold, leaving the universe in complete electromagnetic silence save for the occasional flash of a proton decay event or the Hawking radiation of evaporating black holes. The thermal memory of the Big Bang will persist in principle, but its photons will be so widely separated and low in energy that they will contribute negligibly to the universe's total energy density. Measurements of the background temperature, combined with detailed analysis of its angular power spectrum, enable cosmologists to determine the universe's composition and geometry with remarkable precision. The data indicates that ordinary matter, the stuff of stars, planets, and people, constitutes less than 5% of the total cosmic inventory. Dark matter accounts for roughly 27%, while dark energy dominates at 68%, driving the accelerating expansion discovered through observations of distant supernovae. This cosmic census, derived partly from the acoustic oscillations frozen into the microwave background's temperature patterns, reveals a universe far stranger than early astronomers imagined. The majority of cosmic matter exists in forms that interact gravitationally but remain invisible to electromagnetic radiation, while dark energy operates as a kind of cosmic anti-gravity that pushes space itself apart at ever-increasing rates. As terrestrial temperatures drop through their nocturnal cycle and atmospheric molecules slow their thermal dance, the cosmic microwave background maintains its patient vigil at 725 Kelvin, unchanged by seasons, weather patterns, or the countless geological ages that have transformed Earth's surface. Its photons stream through planetary atmospheres without pause, carrying their ancient thermal signature across the vast emptiness between galaxies, indifferent to the stellar births and deaths, the formation and dissolution of planetary systems, and the brief flickering of biological consciousness that marks the passage of cosmic time in this small corner of an unremarkable galaxy, whose very existence was encoded in those primordial temperature fluctuations detected with such painstaking precision by instruments cooled to within whispers of absolute zero. The European Space Agency's Planck satellite orbits through the darkness at the second Lagrange point, 1.5 million kilometers from Earth, where gravitational forces balance in perfect equilibrium and instruments can operate in the cold silence of deep space. From this vantage point, shielded from terrestrial radio interference and the thermal glow of our planet, Planck's detectors map the cosmic microwave background with a precision that approaches the theoretical limits of measurement. The spacecraft spins slowly, once every minute, sweeping its field of view across the entire celestial sphere while maintaining a constant orientation relative to the Sun and Earth. Planck's instruments operate at temperatures colder than the cosmic background radiation itself, cooled by a sophisticated cryogenic system that brings the most sensitive detectors to just 0.1 Kelvin above absolute zero. At these extreme temperatures, thermal noise from the instruments themselves drops below the faint signal from the primordial universe, allowing the detection of temperature variations that measure in microkelvin, millionths of a degree difference that encode the initial conditions of cosmic evolution. The cooling system represents a triumph of engineering, using multiple stages of refrigeration to achieve temperatures that exist nowhere naturally in the present-day universe. The satellite's high-frequency instrument employs spiderweb bolometers, devices so sensitive they can detect the energy equivalent of a single photon every few seconds. These detectors consist of tiny thermometers suspended on gossamer threads of silicon, designed to absorb microwave radiation and convert its energy into measurable temperature changes. Each detector responds to a slightly different frequency band, allowing scientists to separate the cosmological signal from foreground contamination caused by dust and gas within our own galaxy. Planck's low-frequency instrument uses radio receivers based on high electron mobility transistors, semiconductor devices that amplify extremely weak electromagnetic signals with minimal added noise. These receivers operate in the frequency range where the cosmic microwave background reaches its peak intensity, according to the Planck distribution that describes thermal radiation. The combination of high and low frequency observations enables the construction of detailed maps across 9 different frequency channels, spanning the electromagnetic spectrum from 30 to 857 GHz. The precision of Planck's measurements reveals temperature fluctuations that vary by less than 1 part in 100,000 across the sky, requiring statistical analysis of millions of individual observations to extract meaningful signals from instrumental noise. The spacecraft collected data for 4 years, repeatedly scanning the same regions of sky to improve measurement accuracy through averaging. Each pixel in the final temperature maps represents the accumulated signal from hundreds of individual observations, processed through sophisticated algorithms that account for systematic effects and instrumental characteristics. These maps reveal a cosmic microwave background that appears remarkably uniform at first glance, confirming the isotropy that puzzled early observers. Yet, closer examination uncovers subtle patterns that encode a wealth of information about the universe's composition, geometry, and initial conditions. The temperature variations follow a nearly Gaussian distribution, consistent with primordial fluctuations generated by quantum mechanical processes during cosmic inflation. Deviations from perfect Gaussianity provide tests of inflationary models and potential evidence for more exotic physics in the early universe. The angular power spectrum of temperature fluctuations, a mathematical decomposition that reveals how much structure exists on different angular scales, exhibits a series of acoustic peaks that correspond to sound waves in the primordial plasma. These oscillations began as pressure waves generated by gravity's attempt to compress over-dense regions of matter and radiation. The waves propagated through the early universe at roughly half the speed of light until recombination froze the pattern into the microwave background's temperature field. The first acoustic peak occurs at an angular scale of roughly 1 degree, corresponding to the size of regions that could be causally connected at the time of recombination. This fundamental scale depends on the universe's geometry. In a flat universe, parallel light rays remain parallel over cosmic distances, preserving angular relationships between the early universe and today. The observed position of the first peak provides compelling evidence that space possesses Euclidean geometry on large scales, neither curved inward like a sphere, nor outward like a saddle. Subsequent acoustic peaks appear at smaller angular scales, revealing the harmonic structure of primordial sound waves. The relative heights of these peaks encode information about the cosmic composition, with ordinary matter, dark matter, and dark energy each leaving distinctive signatures in the acoustic oscillations. Ordinary matter contributes to the pressure that drives the waves, while dark matter provides gravitational sources that remain stationary because it interacts only weakly with radiation. The interplay between these components determines the detailed structure of the acoustic peaks. Planck's maps also reveal the polarization properties of the cosmic microwave background, information encoded in the orientation of electromagnetic waves that provides an additional layer of cosmological data. The polarization signal is much weaker than the temperature fluctuations, typically measuring less than 10 microkelvin, but it carries unique information about the early universe's physical conditions. Thomson, scattering of photons by free electrons, naturally produces polarization patterns that correlate with the underlying density field. The polarization maps show two distinct types of patterns: E modes, which curl around temperature fluctuations like electric field lines around charges, and B modes, which exhibit a rotational structure like magnetic field lines. E-mode polarization arises naturally from the acoustic oscillations that create temperature fluctuations, while B-mode polarization requires additional physical processes such as gravitational waves or gravitational lensing by large-scale structure. The search for primordial B-mode polarization represents one of modern cosmology's most ambitious observational challenges, seeking to detect the signature of gravitational waves generated during cosmic inflation. These ripples in space-time itself would have propagated through the early universe, leaving a distinctive imprint on the polarization pattern of the cosmic microwave background. The B-mode signal from inflation would be extraordinarily weak, requiring instruments even more sensitive than Planck and careful separation from contaminating signals produced by galactic dust and other astrophysical sources. Planck's temperature and polarization maps have been analyzed using sophisticated statistical techniques that extract cosmological parameters with unprecedented precision. The data indicates that the universe is 13,799 billion years old, with an uncertainty of only 21 million years. The cosmic inventory consists of 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy, proportions determined by fitting theoretical models to the observed acoustic peak structure. The maps also reveal anomalies that challenge the standard cosmological model's assumptions about statistical isotropy and Gaussianity. Certain features appear larger than expected by chance, including a prominent cold spot in the southern sky and alignments between multipole moments that suggest possible preferred directions in the cosmic microwave background. These anomalies might represent signatures of exotic physics, systematic effects in the data analysis, or simply statistical fluctuations that appear unusual in our particular realization of the cosmic initial conditions. The Planck mission's legacy extends beyond its primary scientific objectives to include technological innovations that advance the frontiers of precision measurement, the satellite's cooling systems, detector technologies, and data analysis methods have applications in quantum physics, materials science, and other fields that require the detection of extremely weak signals in the presence of noise. The mission demonstrates humanity's capacity to measure the universe's properties with remarkable accuracy using instruments that push the boundaries of what is physically possible. As the Planck satellite continues its silent orbit at the Lagrange point, its instruments no longer collecting data but its scientific impact still unfolding through ongoing analysis. The cosmic microwave background maintains its ancient testimony across the sky. The photons detected by Planck's exquisitely sensitive bolometers carry information from the universe's earliest transparent moments, when space itself first became clear enough for light to travel freely across cosmic distances. Each temperature measurement represents a pixel in humanity's most detailed portrait of the infant universe, a map that reveals both the seeds of cosmic structure and the fundamental parameters that govern reality's deepest architecture. The quantum realm operates according to principles that defy everyday intuition, yet its influence extends across cosmic scales to shape the largest structures in the observable universe. In the earliest moments after the Big Bang, when the cosmos measured smaller than a proton and temperatures exceeded the energy scales of particle accelerators, quantum mechanical uncertainty governed the distribution of matter and energy. These microscopic fluctuations in the primordial quantum fields would eventually stretch across billions of light years, becoming the architectural framework for galaxies, clusters, and the vast cosmic web that connects them. Quantum mechanics describes a universe where particles exist in states of probability rather than certainty, where the very act of measurement influences physical outcomes, and where empty space itself seethes with virtual particles that blink in and out of existence on timescales shorter than the smallest measurable intervals. During cosmic inflation, this quantum foam underwent extraordinary magnification, with fluctuations that initially spanned distances smaller than atomic nuclei, expanding to encompass regions larger than stellar systems in less time than light takes to cross a hydrogen atom. The Heisenberg uncertainty principle, which states that certain pairs of physical properties cannot be simultaneously measured with perfect precision, operates continuously throughout the quantum vacuum. Energy and time, position and momentum, and other complementary variables engage in a perpetual dance of uncertainty that prevents the universe from achieving perfect uniformity. These quantum fluctuations persist even at absolute zero temperature, representing the irreducible minimum energy that quantum fields must possess according to the fundamental laws of physics. In the inflationary epoch, space-time itself expanded exponentially, doubling in size every 10 circumflex 37 seconds and continuing this explosive growth for perhaps 10 circumflex 32 seconds total. During this brief interval, quantum fluctuations that initially existed on scales comparable to the Planck length, 10 circumflex 35 meters, the smallest meaningful distance in physics, stretched to macroscopic proportions. The process resembled inflating a balloon with quantum static painted on its surface, magnifying microscopic patterns until they become visible to cosmic observers billions of years later. The scalar field that drove inflation, known as the inflaton, possessed its own quantum fluctuations that varied randomly from point to point throughout space. These variations followed a nearly scale-invariant spectrum, meaning that fluctuations on different size scales possess similar amplitudes when measured appropriately. This property results from the exponential expansion during inflation, which stretches fluctuations beyond the cosmic horizon and freezes them in amplitude until they re-enter the observable universe at later epochs. As each quantum fluctuation crossed outside the horizon during inflation, it ceased evolving dynamically and became a classical perturbation in the matter and energy density. These frozen fluctuations waited patiently while inflation ended. The universe reheated through the decay of the inflaton field, and the cosmos entered the radiation-dominated era characterized by the thermal equilibrium of particles and antiparticles. Only after recombination, when the cosmic microwave background decoupled from matter, did these primordial seeds begin their gravitational collapse toward the formation of structure. The statistical properties of quantum fluctuations imprint themselves directly onto the cosmic microwave background's temperature and polarization patterns. The fluctuations follow a Gaussian distribution, reflecting the random nature of quantum mechanical processes, with the amplitude of variations determined by the energy scale of inflation. Measurements of the microwave background's statistical properties thus provide a direct observational window into quantum physics operating under the most extreme conditions imaginable. Non-Gaussianity in the cosmic microwave background, Deviations from the perfectly random distribution expected for linear quantum fluctuations could reveal evidence for more complex physics during the inflationary epoch. Multiple scalar fields, interactions between the inflaton and other quantum fields, or modifications to Einstein's general relativity might generate distinctive non-Gaussian signatures that persist in the observable temperature patterns. Current observations indicate that any non-Gaussianity must be extremely small, consistent with the simplest inflationary models, but providing stringent constraints on alternatives. The quantum fluctuations that seeded cosmic structure operate across an enormous range of physical scales, from the smallest wavelengths that could fit within the inflationary horizon to the largest modes that encompass the entire observable universe. Each scale corresponds to fluctuations that crossed outside the horizon at different times during inflation, creating a spectrum of perturbations with slightly different amplitudes and phases. The superposition of all these modes creates the complex pattern of hot and cold spots observed in the cosmic microwave background. Quantum field theory predicts that these primordial fluctuations should be adiabatic, meaning that the fractional density perturbations in different types of matter, ordinary matter, dark matter, and radiation, maintain constant ratios throughout space. This property arises naturally from single-field inflation models, where a single quantum field drives both the exponential expansion and generates the primordial fluctuations. Alternative models involving multiple fields might produce isocurvature fluctuations, where the relative densities of different matter types vary independently, but observations strongly favor the adiabatic scenario. The quantum origin of cosmic structure represents one of physics' most remarkable connections between the microscopic and macroscopic realms. Laboratory experiments routinely demonstrate quantum effects on atomic scales, while astronomical observations reveal their consequences across cosmic distances. The same mathematical formalism that describes electron behavior in hydrogen atoms governs the statistical properties of galaxy clustering and the angular power spectrum of temperature fluctuations in the cosmic microwave background. Modern quantum field theory extends these connections to even more exotic possibilities, suggesting that vacuum fluctuations during inflation might have generated primordial gravitational waves, ripples in space-time itself that propagated through the early universe at light speed. These gravitational wave backgrounds would leave distinctive signatures in the polarization patterns of the cosmic microwave background, specifically in the B-mode polarization that results from the tensor nature of gravitational perturbations. The amplitude of primordial gravitational waves depends on the energy scale of inflation, providing a potential observational probe of physics at energies far beyond those accessible to terrestrial particle accelerators. If inflation occurred near the Planck scale, where quantum gravity effects become important, the resulting gravitational wave background might be detectable by future cosmic microwave background polarization experiments. Such a discovery would represent the first direct observation of quantum gravitational phenomena. Quantum fluctuations continue to influence cosmic evolution even after inflation ends and the universe enters more familiar physical regimes. During the radiation-dominated era, acoustic oscillations in the photon-baryon plasma amplify and suppress density perturbations on different scales, creating the peak structure observed in the cosmic microwave background's angular power spectrum. These oscillations themselves arise from the interplay between quantum-generated initial conditions and classical fluid dynamics in the primordial plasma. The quantum vacuum also contributes to the cosmic microwave background through the Casimir effect, where virtual particles create pressure differences between regions with different boundary conditions. Though this effect operates primarily on microscopic scales in laboratory settings, it might have influenced the evolution of cosmic structure during phase transitions in the early universe. When symmetry breaking created effective boundaries between different vacuum states, entanglement, perhaps quantum mechanics' most mysterious property, may have played a role in establishing the correlations observed between widely separated regions of the cosmic microwave background. If inflation stretched entangled quantum states to cosmic proportions, the resulting correlations might persist in the temperature and polarization patterns we observe today. Some theoretical models suggest that these quantum correlations could leave observable signatures that distinguish inflationary scenarios from alternative theories of the early universe. The measurement of cosmic microwave background fluctuations represents a macroscopic quantum measurement, where the collapse of quantum superposition states occurred when photons last scattered from free electrons during recombination. The resulting classical temperature and polarization patterns preserve information about the quantum state of the early universe. Much like the measurement of a quantum system's properties collapses its wave function into definite values. This cosmic measurement process occurred naturally through the physical interactions that establish thermal equilibrium in the primordial plasma. As consciousness settles into the quiet rhythm of rest, quantum fluctuations continue their eternal dance in the vacuum that surrounds and permeates all matter. The same uncertainty principle that prevents precise, simultaneous measurement of position and momentum ensures that empty space can never be truly empty. Bubbling continuously with virtual particles that appear and disappear on timescales shorter than direct observation, these quantum whispers, amplified by cosmic inflation to astronomical proportions, shape the distribution of matter and energy that would eventually give rise to stars, planets, and the complex chemistry of life itself. Connecting the deepest mysteries of quantum mechanics to the grandest structures visible in the cosmic microwave background's ancient light. Sound travels through the primordial plasma at nearly half the speed of light, creating acoustic waves that propagate across cosmic distances during the universe's first few 100,000 years. These pressure oscillations arise from the gravitational compression of overdense regions, which squeeze matter and radiation together until internal pressure forces resist further collapse. The resulting waves bounce back and forth like sound reverberating in a vast cosmic chamber, establishing standing wave patterns that will eventually freeze into the temperature fluctuations observed in the cosmic microwave background. The speed of these primordial sound waves depends on the ratio of pressure to density in the photon-baryon fluid, a quantity determined by the fundamental physics of radiation and matter interactions. In the early universe, photons carry most of the energy, while baryonic matter provides relatively little mass, creating a cosmic medium where sound propagates at roughly 57% of light speed. This acoustic velocity remains remarkably constant throughout the pre-recombination epoch, varying only slightly as the universe expands and cools toward the moment when atoms first form. Gravitational potential wells, created by the initial density perturbations from inflation, act as acoustic sources that drive the oscillating plasma. Matter falls into these wells, compressing the photon-baryon fluid and increasing both its density and temperature. The elevated pressure then pushes the fluid back out of the gravitational well, creating a rarefaction that propagates outward as an acoustic wave. This process repeats continuously, with different wavelength modes oscillating at frequencies determined by their size and the cosmic expansion rate. The acoustic oscillations follow predictable patterns governed by the wave equation for a relativistic fluid in an expanding spacetime. Compression phases correspond to maximum density and temperature, while rarefaction phases represent minimum values. The oscillations maintain coherent phase relationships across vast distances because all regions of the universe began oscillating simultaneously when inflation ended and gravitational instability began driving the collapse of overdense regions. Each wavelength of acoustic oscillation completes a different number of cycles between the end of inflation and the epoch of recombination. Modes that undergo an odd number of half cycles reach maximum compression at the moment of last scattering, appearing as hotspots in the cosmic microwave background. Modes that complete an even number of half cycles reach maximum rarefaction, appearing as cold spots. This alternating pattern creates the series of acoustic peaks observed in the angular power spectrum of temperature fluctuations. The physical scale of the acoustic oscillations at recombination corresponds to the sound horizon, the maximum distance that acoustic waves could have traveled since the Big Bang. This fundamental length scale equals approximately 150 megaparsecs in comoving coordinates, corresponding to an angular size of roughly 1 degree on the sky as observed today. The sound horizon sets the characteristic scale for the largest coherent temperature fluctuations in the cosmic microwave background, appearing as the first and most prominent peak in the angular power spectrum. Smaller angular scales correspond to higher-order acoustic harmonics, where multiple wavelengths fit within the sound horizon and create more complex interference patterns. These harmonic peaks encode detailed information about the universe's composition and geometry, with peak positions determined by the cosmic matter density and peak heights influenced by the relative abundances of ordinary matter, dark matter, and radiation. The precise measurement of multiple acoustic peaks enables cosmologists to determine fundamental parameters with remarkable accuracy. The Doppler effect influences the acoustic oscillations as different regions of the photon-baryon fluid move toward and away from observers with velocities up to half the speed of light. Regions undergoing compression move toward lower gravitational potential, blue shifting the radiation they emit, while regions in rarefaction move toward higher potential, red shifting their light. These velocity-induced temperature shifts add to the density-induced fluctuations, creating complex correlations between temperature and polarization patterns in the cosmic microwave background. Viscous damping gradually attenuates the acoustic oscillations on small scales, where photon diffusion becomes efficient enough to smooth out temperature differences. This Silk damping, named after astronomer Joseph Silk, who first calculated the effect, operates through the random walk of photons between scattering events with free electrons. The mean free path for photon-electron scattering sets the damping scale, typically corresponding to angular sizes of several arc-minutes in the cosmic microwave background observations. The acoustic waves carry information about physical conditions throughout the pre-recombination universe, encoding the history of cosmic expansion, the evolution of matter and radiation densities, and the effects of exotic physics that might have operated during the early epochs. Precise measurements of the acoustic peak structure thus provide observational tests of cosmological models and potential evidence for physics beyond the standard paradigm of particle physics and general relativity. Baryon acoustic oscillations continue to influence cosmic structure formation long after recombination, when matter decouples from radiation and begins collapsing under gravity alone. The acoustic waves imprint a preferred scale on the matter distribution, creating slightly enhanced clustering at distances corresponding to the sound horizon at recombination. This baryon acoustic oscillation feature appears in galaxy surveys as a subtle excess of galaxy pairs separated by roughly 150 megaparsecs, providing an independent confirmation of the acoustic physics encoded in the cosmic microwave background. The three-dimensional matter distribution preserves the acoustic signature across cosmic time, allowing astronomers to trace the expansion history of the universe through observations of galaxy clustering at different redshifts. The baryon acoustic oscillation scale serves as a standard ruler for cosmological distance measurements, analogous to the way supernovae serve as standard candles for determining cosmic acceleration. Together, these observations reveal a universe dominated by dark energy that drives accelerating expansion. Neutrino free streaming modifies the acoustic oscillations by removing relativistic particles from the photon-baryon fluid before recombination occurs. Massive neutrinos decouple from the thermal plasma when the universe cools below their rest mass energy, reducing the effective radiation density that contributes to acoustic wave propagation. The resulting shifts in peak positions and heights provide observational constraints on neutrino masses and the number of neutrino species, connecting cosmic microwave background observations to fundamental particle physics. The acoustic oscillations also interact with magnetic fields that might have existed in the primordial plasma, though observations indicate that any such fields must have been extremely weak. Strong magnetic fields would have provided additional pressure support that altered the acoustic wave propagation, shifting peak positions and creating distinctive signatures in the polarization patterns. Current limits on these effects constrain primordial magnetic fields to strengths far below those observed in galaxies today. Dark matter participates in the gravitational dynamics that drive acoustic oscillations, but does not contribute directly to the pressure that propagates the waves. This fundamental difference between dark matter's gravitational effects and its lack of electromagnetic interactions creates phase shifts between the oscillations in dark matter and baryonic matter, measurable through their combined gravitational effects on photon geodesics. The interplay between dark and ordinary matter provides crucial evidence for the existence of non-baryonic matter in the early universe. Primordial gravitational waves, if they exist, would contribute their own acoustic signature to the cosmic microwave background through the oscillatory expansion and contraction of space itself. These tensor perturbations propagate at light speed and create temperature and polarization patterns that differ subtly from those generated by scalar density perturbations. The detection of such gravitational wave signatures would provide direct evidence for cosmic inflation and probe the energy scale at which it occurred. As the universe expanded and cooled toward recombination, the acoustic oscillations gradually decreased in amplitude due to the declining efficiency of photon-matter coupling. The Thomson scattering cross-section remains constant, but the decreasing density of free electrons reduces the interaction rate until photons begin to stream freely through space. The final phases of acoustic oscillation occur as the cosmic microwave background decouples from matter, freezing the wave patterns into the temperature and polarization distributions observed today. Modern computer simulations recreate the acoustic oscillation process using the fundamental equations of relativistic hydrodynamics and quantum field theory, following the evolution of perturbations from their quantum mechanical origins through recombination and beyond. These calculations require enormous computational resources to capture the full complexity of the acoustic physics while maintaining sufficient numerical resolution to predict observational signatures accurately. The agreement between theoretical predictions and cosmic microwave background observations represents one of modern cosmology's most successful theoretical achievements. The acoustic oscillations in the cosmic microwave background represent the universe's first and most fundamental music, pressure waves propagating through the primordial medium at nearly the speed of light, creating harmonic patterns that encode the cosmic composition, geometry, and initial conditions. These frozen sound waves, preserved in the temperature fluctuations of ancient light, continue to reverberate through space as galaxies form, stars ignite, and conscious observers develop the technology to detect and decode their message. Listening carefully to the cosmic symphony that began playing in the universe's first moments and whose echoes still whisper through the quantum vacuum that surrounds every atom in existence. Dark matter weaves its invisible influence through the cosmic microwave background, leaving gravitational fingerprints that reveal the presence of matter that interacts with ordinary particles only through the fundamental force that shapes space-time itself. This mysterious substance, comprising roughly 85% of all matter in the universe, participated fully in the gravitational dynamics that drove acoustic oscillations in the primordial plasma, yet remained completely decoupled from the electromagnetic interactions that scattered photons and coupled them to baryonic matter during the pre-recombination epoch. The gravitational lensing of cosmic microwave background photons by intervening dark matter structures creates subtle distortions in the temperature and polarization patterns that astronomers observe today. These ancient photons, traveling for nearly 14 billion years from the surface of last scattering, encounter dark matter halos, filaments, and voids that deflect their paths by tiny angles measured in arcminutes. The cumulative effect of billions of such deflections smears the primordial temperature patterns, creating correlations between different angular scales that would not exist in an unlensed sky. The lensing signal encodes information about the distribution of dark matter along the entire line of sight from recombination to the present epoch, providing a three-dimensional map of invisible structure spanning cosmic history. Dense concentrations of dark matter focus the cosmic microwave background photons like gravitational telescopes, creating slight magnifications in some regions while defocusing others. The statistical analysis of these lensing distortions reveals how dark matter clusters evolved under gravity's influence, growing from tiny primordial fluctuations into the cosmic web of filaments and nodes observed in galaxy surveys. Weak gravitational lensing operates through Einstein's general relativity, which describes gravity not as a force, but as the curvature of space-time caused by the presence of matter and energy. Massive objects bend the fabric of space and time, creating curved paths for light rays that would otherwise travel in straight lines through empty space. The deflection angles depend on the mass of the lensing object and the geometry of the configuration, allowing astronomers to weigh dark matter structures without relying on their electromagnetic emissions. The lensing of cosmic microwave background polarization creates distinctive patterns that differ from those generated by primordial gravitational waves or other physical processes. Lensing converts the curl-free E-mode polarization into rotational B-mode patterns through the mixing of different Fourier modes, creating correlations that can be detected through sophisticated statistical analysis. This lensing B-mode signal has been measured with high significance by multiple experiments, providing direct evidence for dark matter's gravitational effects on the cosmic microwave background. Dark matter's influence on acoustic oscillations appears through phase shifts between the oscillations in matter and radiation components of the primordial fluid. While photons and baryons oscillated together as a tightly coupled system, dark matter responded only to gravitational forces and remained essentially stationary in the gravitational potential wells created by primordial density perturbations. This fundamental difference in physical behavior creates measurable effects in the acoustic peak structure that constrain the dark matter abundance with remarkable precision. The interaction between dark matter and ordinary matter during the acoustic oscillation epoch reveals itself through the relative heights of odd and even acoustic peaks in the cosmic microwave background power spectrum. Dark matter provides additional gravitational sources that enhance the compression phases of acoustic oscillations while having minimal effect on rarefaction phases, creating asymmetries in peak heights that depend on the dark matter density. The measured peak ratios indicate that dark matter outweighs ordinary matter by roughly 5-to-1 throughout cosmic history. Sterile neutrinos, hypothetical particles that interact only gravitationally, represent one candidate for dark matter that could have influenced the cosmic microwave background through their contribution to the radiation density during the acoustic oscillation epoch. If sterile neutrinos possess masses in the keV range and were produced thermally in the early universe, they would have decoupled from the primordial plasma at temperatures around 100 MeV, behaving as dark radiation during nucleosynthesis but as dark matter during structure formation. The cosmic microwave background places stringent limits on the properties of dark matter particles through their potential effects on recombination and acoustic oscillations. Strongly interacting dark matter would have coupled to the photon-baryon fluid, modifying the sound speed and damping properties of acoustic waves. Annihilating dark matter would inject energy into the primordial plasma, ionizing hydrogen atoms and delaying recombination. Current observations rule out most exotic dark matter models while remaining consistent with weakly interacting massive particles. Primordial black holes, if they formed in sufficient numbers during the early universe, could contribute to dark matter while creating distinctive signatures in the cosmic microwave background through their gravitational effects and Hawking radiation. Black holes with masses around 10 circumflex 15 grams would be evaporating through Hawking radiation at the present epoch, producing high-energy particles that could ionize the intergalactic medium and create spectral distortions in the cosmic microwave background. The absence of such distortions constrains primordial black holes as a major component of dark matter. The small-scale structure of dark matter influences cosmic microwave background lensing through the abundance and internal profiles of dark matter halos. Cold dark matter models predict a hierarchy of structure extending to very small scales, with numerous low-mass halos contributing to the lensing signal. Warm dark matter, composed of particles with higher velocities, would suppress structure formation below a characteristic scale determined by the particle mass, creating measurable differences in the lensing power spectrum. Self-interacting dark matter models propose that dark matter particles scatter off each other through forces beyond gravity, potentially resolving discrepancies between cold dark matter simulations and observations of galaxy and cluster cores. Strong self-interactions would modify the acoustic oscillations by providing additional pressure support in dark matter perturbations, creating phase shifts and damping effects that could be detected in precision cosmic microwave background measurements. Axion dark matter, consisting of ultralight bosonic particles, would create oscillating gravitational potentials that modulate the cosmic microwave background temperature through the integrated Sachs-Wolf effect. These oscillations occur at frequencies determined by the axion mass and could produce periodic features in the cosmic microwave background power spectrum. Current searches for such signals provide constraints on axion, dark matter models, while exploring fundamental physics at energy scales far beyond laboratory experiments. The cosmic microwave background lensing maps reveal dark matter structures that remain invisible to electromagnetic observations, tracing filaments and voids that connect and separate visible galaxies. These lensing reconstructions show dark matter concentrations that sometimes align with galaxy clusters, but also reveal significant amounts of dark matter in apparently empty regions of space. The correlation between dark matter and luminous matter provides insights into galaxy formation processes and the role of feedback from stars and supermassive black holes. Cross-correlations between cosmic microwave background lensing and galaxy surveys provide independent measurements of cosmic structure, growth, and dark matter clustering. The statistical relationship between dark matter and galaxy distributions depends on the bias factor that relates luminous and dark matter fluctuations, a quantity that evolves with cosmic time as galaxies form and evolve within dark matter halos. These cross-correlation studies test models of galaxy formation while constraining dark energy and modified gravity theories. The lensing of cosmic microwave background photons continues to increase as the universe ages and dark matter structures grow through gravitational collapse. Future observations will detect this temporal evolution through measurements of cosmic microwave background lensing at different effective redshifts, providing direct tests of dark matter, clustering theories, and constraints on dark energy properties. The lensing signal thus serves as a time machine that reveals how invisible structure assembled throughout cosmic history. Gravitational waves from merging black holes and neutron stars propagate through the dark matter distribution without significant interaction, providing complementary probes of cosmic structure that operate independently of electromagnetic observations. The combination of gravitational wave detections, cosmic microwave background lensing measurements, and galaxy surveys will map the dark matter distribution across cosmic time with unprecedented accuracy, revealing how the invisible scaffolding of the universe assembled from quantum fluctuations into the complex structures that govern cosmic evolution. As dark matter particles stream silently through the solar system, the Milky Way, and the vast spaces between galaxies. They continue to gravitationally lens the cosmic microwave background photons that have traveled since recombination. These invisible deflections encode information about every dark matter structure the photons encountered during their 13.8 billion-year journey, creating correlations and distortions in the ancient light that reveal the hidden architecture of the universe through purely gravitational effects that operate according to Einstein's geometric description of gravity in curved spacetime. Polarization whispers through the cosmic microwave background, like light remembering the last scattering events that set it free from matter, encoding information about magnetic fields, electron motions, and the geometric properties of space-time itself in the subtle orientation patterns of electromagnetic waves. The polarization signal measures typically less than 10% of the temperature fluctuations, requiring instruments of extraordinary sensitivity to detect the faint asymmetries in photon polarization, states that preserve evidence of physical conditions during the recombination epoch. Thomson scattering naturally produces polarization when photons interact with free electrons in the presence of temperature or velocity gradients, creating slight preferences for certain electromagnetic field orientations over others. The scattering process operates most efficiently when incoming radiation exhibits quadrupole asymmetries, situations where photons arrive at an electron from different directions with different intensities. These asymmetries existed throughout the recombination epoch as acoustic oscillations created density and velocity variations in the primordial plasma. The polarization patterns divide into two fundamental types with distinct geometric properties and physical origins. E-mode. Polarization exhibits curl-free patterns that resemble electric field lines radiating from charges, creating structures that can be decomposed into gradients of scalar potential fields. B-mode polarization displays rotational patterns similar to magnetic field lines, possessing handedness that cannot be reduced to scalar gradients and requiring more exotic physical processes for their generation. E-mode polarization correlates directly with temperature fluctuations through the acoustic oscillations that drove both density and velocity perturbations in the photon baryon fluid. Hotspots in the cosmic microwave background temperature maps correspond to regions where compression phases of acoustic waves created both enhanced photon density and coherent electron motions. The resulting polarization patterns point radially toward cold spots and tangentially around hotspots, creating the distinctive E-mode signature that has been detected with high confidence by multiple observational programs. The detection of E-mode polarization confirms theoretical predictions about Thomson scattering in the primordial plasma while providing independent constraints on cosmological parameters. The polarization amplitude depends on the optical depth to Thomson scattering during recombination, which relates to the baryon density and the detailed physics of hydrogen and helium ionization. Precise measurements of the E-mode power spectrum thus offer complementary information to temperature observations and help break degeneracies between different cosmological parameters. B-mode polarization presents far greater observational challenges because it requires physical processes that operate beyond the scalar perturbations generated by simple density fluctuations. Tensor perturbations, such as those produced by primordial gravitational waves during cosmic inflation, naturally generate B-mode patterns through their effects on photon geodesics in curved spacetime. The amplitude of this primordial B-mode signal depends on the energy scale of inflation, providing a potential observational window into quantum gravity physics. Gravitational lensing of the cosmic microwave background creates secondary B-mode polarization by mixing E-mode patterns through the deflection of photon paths by dark matter structures. This lensing B-mode signal has been detected by ground-based and satellite experiments, confirming both the lensing of cosmic microwave background photons and the theoretical framework that relates polarization patterns to gravitational effects. The lensing B modes provide information about dark matter distribution and cosmic structure growth, complementary to temperature-based lensing measurements. Reionization of intergalactic hydrogen by the first stars and quasars creates additional polarization signatures through Thomson, scattering of cosmic microwave background photons by free electrons in the reionized medium. This process occurs much later than recombination, typically at redshifts between 6 and 20, and produces large-scale polarization patterns that correlate with the integrated electron density along different lines of sight. The reionization signal appears primarily in E-mode polarization at angular scales larger than several degrees. The search for primordial B-mode polarization requires separating the cosmological signal from contaminating foregrounds produced by synchrotron emission and thermal dust in our own galaxy. Galactic synchrotron radiation, generated by relativistic electrons spiraling in magnetic fields, exhibits intrinsic polarization that can mimic the B-mode signature of gravitational waves. Polarized thermal emission from aligned dust grains creates additional contamination that becomes increasingly problematic at the high frequencies where the cosmic microwave background reaches peak intensity. Sophisticated component separation techniques employ observations at multiple frequencies to distinguish cosmological signals from galactic foregrounds based on their different spectral properties. The cosmic microwave background exhibits a black-body spectrum that peaks near 150 GHz, while synchrotron emission decreases toward higher frequencies and dust emission increases. Statistical analysis of polarization maps across frequency bands enables the reconstruction of the underlying cosmological signal with quantified uncertainties. The cosmic microwave background polarization encodes information about magnetic fields that might have existed in the primordial universe, though current observations indicate that any such fields must have been extremely weak. Strong primordial magnetic fields would have contributed additional pressure support during acoustic oscillations, while also generating their own polarization signatures through Faraday rotation and magnetic field-induced anisotropies. The absence of such effects constrains primordial magnetism to levels well below those observed in present-day galaxies. Polarization observations provide tests of fundamental physics through their sensitivity to parity-violating processes that could rotate the polarization plane of propagating photons. Such effects might arise from interactions between photons and pseudoscalar fields, like axions, creating systematic rotations that would appear as correlations between E-mode and B-mode polarization patterns. The measurement of cosmic birefringence through these correlations offers potential evidence for new physics beyond the standard model of particle physics. The polarization patterns preserve information about the velocity structure of the primordial plasma during recombination, encoding the Doppler shifts and peculiar motions that accompanied acoustic oscillations. Moving electrons scatter photons with slightly shifted frequencies and altered polarization properties, creating correlations between temperature and polarization that depend on the acoustic wave phases at the moment of last scattering. These velocity-induced signatures provide additional constraints on the acoustic physics and cosmic geometry. Future cosmic microwave background polarization experiments aim to achieve the sensitivity required to detect primordial B-mode signals from cosmic inflation, potentially revealing gravitational wave backgrounds with amplitudes as small as a few tens of nanokelvin in equivalent temperature fluctuations. Such measurements would probe the energy scale of inflation directly, potentially reaching energies near the Planck scale where quantum gravity effects become important. The detection of inflationary B modes would represent one of the most significant discoveries in fundamental physics. The statistical analysis of cosmic microwave background polarization requires sophisticated mathematical techniques to separate the E-mode and B-mode components while accounting for instrumental effects, systematic errors, and incomplete sky coverage. Pure E and B estimators minimize the leakage between different polarization modes, while maximum likelihood methods optimally weight the available data to extract cosmological parameters. Monte Carlo simulations test analysis pipelines and quantify statistical uncertainties in parameter estimation. Ground-based polarization experiments exploit atmospheric windows at millimeter wavelengths, deploying thousands of superconducting detectors at high-altitude sites chosen for their low atmospheric water vapor and stable weather conditions. The Atacama Desert in Chile and the South Pole provide ideal observing locations where precipitable water vapor remains below 1 millimeter for significant fractions of the year. These experiments achieve unprecedented sensitivity through advances in detector technology, cryogenic systems, and telescope design. Balloon-borne and satellite missions extend polarization observations to frequency bands inaccessible from the ground while avoiding atmospheric contamination and achieving full sky coverage. The Planck satellite measured cosmic microwave background polarization across 9 frequency bands, creating the most comprehensive polarization maps available and setting the current best limits on primordial B-mode signals. Future satellite missions will push sensitivity to the levels required for detecting inflation-generated gravitational waves. The polarization of the cosmic microwave background continues its patient testimony about the early universe's physical conditions, carrying information about electron motions, magnetic fields, and gravitational waves across 13.8 billion years of cosmic expansion. Each polarized photon preserves the memory of its last interaction with free electrons during recombination, maintaining its electromagnetic field orientation through the vast journey from the surface of last scattering to present-day detectors that measure its arrival direction and polarization state with exquisite precision. Cold spots punctuate the cosmic microwave background's temperature map like islands of relative coolness in an ocean of ancient light, representing regions where photons have lost energy climbing out of gravitational potential wells or traveling through vast cosmic voids that stretch across hundreds of millions of light years. The largest of these anomalies spans roughly 10 degrees on the sky, an angular size 20 times wider than the full moon, and exhibits temperatures that measure 70 microkelvin below the cosmic average, making it statistically significant enough to challenge assumptions about cosmic uniformity. The cold spot, formerly known as the cosmic microwave background cold spot, occupies a region of the southern hemisphere sky in the direction of the constellation Eridanus, where multiple observational surveys have confirmed its anomalous properties through independent measurements. The feature appears not as a simple circular depression, but as a complex structure with multiple cold regions separated by warmer areas. Suggesting a complicated three-dimensional origin rather than a simple spherical void, its irregular morphology and large angular extent distinguish it from the smaller, more circular temperature fluctuations that dominate most of the cosmic microwave background. Supervoids, enormous regions of space with densities significantly below the cosmic average, may explain some cold spots through the integrated Sachs-Wolf effect, which occurs when cosmic microwave background photons travel through time-varying gravitational potential wells. As the universe expands and dark energy drives accelerating cosmic expansion, gravitational potential wells become shallower over time. Photons that fall into potential wells gain energy, but if the wells become shallower during the photon's transit time, they cannot recover all their energy when climbing back out, resulting in a net redshift that appears as cooling in the temperature maps. The largest known supervoid. The Bootes void spans roughly 330 million light-years in diameter and contains significantly fewer galaxies than typical regions of space at similar distances. Cosmic microwave background photons passing through such vast underdense regions experience the integrated Sachs-Wolf effect as dark energy causes the void's gravitational potential to decay over cosmic time. However, detailed calculations suggest that even the largest known voids cannot fully account for the most extreme cold spots observed, indicating that additional physical processes or statistical fluctuations may contribute to these anomalies. Primordial origins offer alternative explanations for cold spots that extend beyond simple gravitational effects from large-scale structure. Non-Gaussian features in the primordial density field, generated by exotic physics during cosmic inflation or other early universe processes, could create temperature anomalies that appear statistically unlikely under the assumption of purely Gaussian initial conditions. Such features might result from phase transitions, cosmic strings, or other topological defects that existed during the universe's earliest moments. The statistics of cosmic microwave background temperature fluctuations follow a nearly Gaussian distribution, consistent with the quantum mechanical origin of primordial density perturbations during cosmic inflation. However, the cold spot and other large-scale anomalies represent deviations from perfect Gaussianity that occur with probabilities low enough to merit careful investigation. The probability of observing a cold spot as large and deep as the one detected is roughly 1% under standard cosmological models, making it an interesting outlier but not necessarily evidence for exotic physics. Topological defects. Hypothetical structures formed during symmetry-breaking phase transitions in the early universe could create distinctive signatures in the cosmic microwave background, including localized cold or hot spots. Cosmic strings, one-dimensional defects with enormous linear mass density, would create characteristic temperature patterns as they move through space at relativistic velocities. The interaction between cosmic strings and cosmic microwave background photons produces step function temperature discontinuities that appear as sharp edges in temperature maps, quite different from the smooth Gaussian fluctuations expected from inflation. Textures. Three-dimensional topological defects that collapse and annihilate over cosmic time represent another class of exotic objects that could generate cold spots through their gravitational effects on passing photons. Unlike cosmic strings, which persist indefinitely, textures have finite lifetimes and disappear when their characteristic size becomes comparable to their Compton wavelength. The collapse of a texture creates a spherical wave of gravitational potential that produces both hot and cold regions in the cosmic microwave background, with the specific pattern depending on the texture's mass and collapse time. Colliding bubble cosmology, which envisions our observable universe as existing within a bubble of broken symmetry that collides with other bubbles in a higher dimensional space, predicts distinctive signatures, including circular temperature anomalies in the cosmic microwave background. Such collisions would create correlated hot and cold regions with specific geometric relationships that differ from the random patterns expected from Gaussian initial conditions. Searches for these collision signatures have yielded tentative candidates, but no definitive detections. Void models of dark energy propose that our observable universe occupies a large, underdense region embedded in a denser cosmic background, potentially explaining the observed acceleration without requiring exotic dark energy components. In such models, cosmic microwave background photons originating from different directions would have traveled through regions with different expansion histories, creating systematic temperature variations that might manifest as cold spots or other large-scale anomalies. However, most void models face difficulties explaining the high degree of isotropy observed in the cosmic microwave background. Statistical analysis of cold spots requires sophisticated methods to account for the look elsewhere effect, which inflates the apparent significance of anomalies when searching across large datasets. The probability of finding at least one cold spot of a given size somewhere in the cosmic microwave background sky is much higher than the probability of finding it in a specific predetermined location. Proper statistical treatment requires specifying search criteria in advance and correcting for multiple comparisons across different locations, angular scales, and significance thresholds. The morphology of cold spots provides additional information beyond their temperature profiles, with shape analysis revealing details about their three-dimensional structure and potential origins. Spherically, symmetric cold spots suggest simple void-like structures, while elongated or irregular features may indicate more complex formation mechanisms such as filamentary voids, projection effects from multiple structures along the line of sight, or primordial non-Gaussianities with specific geometric properties. Polarization measurements in cold spot regions offer complementary tests of different formation scenarios. Since various physical processes predict different relationships between temperature and polarization anomalies, voids and other gravitational effects typically produce minimal polarization signatures, while primordial mechanisms like cosmic strings or textures create characteristic polarization patterns that correlate with their temperature features. The absence of strong polarization signals in most cold spots supports gravitational explanations over more exotic alternatives. Cross-correlations between cosmic microwave background cold spots and galaxy surveys provide direct tests of the supervoid hypothesis by identifying underdense regions along the lines of sight toward temperature anomalies. Several studies have found evidence for enhanced void populations in directions of prominent cold spots, supporting the integrated Sachs-Wolf interpretation while constraining the void properties required to explain the observed temperature depressions. However, the correlations are not always strong enough to fully account for the largest anomalies. Future observations will provide definitive tests of cold spot origins through improved sensitivity, higher angular resolution, and better systematic error control. Next-generation cosmic microwave background experiments will map temperature and polarization fluctuations with unprecedented precision across multiple frequency bands, enabling more accurate separation of primordial signals from foreground contamination. Space-based missions will achieve full sky coverage without atmospheric interference, providing the data quality needed to resolve debates about anomalous features. The cosmic microwave background continues to reveal its cold spots across the celestial sphere, marking regions where ancient photons lost energy during their 13.8 billion-year journey from recombination to present-day detectors. These temperature depressions encode information about large-scale cosmic structure, early universe physics, and the statistical properties of quantum fluctuations that seeded all subsequent cosmic evolution, creating a permanent record of the universe's thermal history written in the subtle variations of primordial light that streams through every corner of space. Axis alignments in the cosmic microwave background challenge the fundamental cosmological principle that assumes the universe appears statistically identical in all directions when viewed on the largest scales, revealing patterns that seem to violate the expected isotropy of primordial quantum fluctuations. The alignments involve correlations between temperature fluctuations on vastly different angular scales, from the largest features spanning tens of degrees to smaller structures measuring just a few degrees across. These correlations appear with probabilities low enough that astronomers have provocatively labeled them the axis of evil, reflecting scientific discomfort with observations that resist conventional theoretical explanations. The quadrupole and octupole moments of the cosmic microwave background temperature distribution, mathematical quantities that describe the spherical harmonic components corresponding to the largest angular scales, exhibit a surprising degree of alignment with each other and with features of the local cosmic environment. Under the assumption of statistically isotropic initial conditions, these low-order multipole moments should point in random directions with no preferred orientation. Instead, observations reveal alignments that occur with probabilities of roughly 1% or less, depending on the specific statistical tests applied. The ecliptic plane, which defines the orbital motion of Earth around the Sun, shows unexpected correlations with the cosmic microwave background's largest scale temperature patterns, suggesting either systematic contamination from solar system effects or a genuine cosmological asymmetry that happens to align with local astronomical coordinates. The quadrupole moment's orientation lies suspiciously close to the ecliptic plane, while higher-order multipoles show weaker but still statistically significant correlations with the same geometric reference frame. Galactic contamination represents the most prosaic explanation for these alignments, arising from imperfect subtraction of foreground emission from dust, synchrotron radiation, and other astrophysical sources within the Milky Way. Despite sophisticated component separation techniques that use observations at multiple frequencies to distinguish cosmological signals from galactic contributions, subtle residuals may persist and create artificial correlations between the cosmic microwave background and local astronomical reference frames defined by our location within the galaxy. The cosmic dipole, which results from our solar system's motion through the cosmic rest frame at 370 kilometers per second, creates a temperature asymmetry of roughly 3.4 millikelvin between opposite hemispheres of the sky. Interactions between this kinematic dipole and instrument systematics, data processing algorithms, or residual foreground contamination could potentially generate spurious correlations at larger angular scales. However, detailed analysis suggests that such effects cannot fully explain the observed alignments without invoking implausibly large systematic errors. Primordial anisotropy offers a more exotic explanation involving genuine departures from statistical isotropy in the initial conditions that seeded cosmic structure formation. Such anisotropies might arise from cosmic inflation occurring in the presence of vector fields, multiple scalar fields with preferred orientations, or modifications to general relativity that break rotational symmetry. These scenarios predict specific patterns of statistical anisotropy that can be tested through detailed analysis of cosmic microwave background temperature and polarization maps. The Bianchi models represent a class of cosmological solutions to Einstein's field equations that possess preferred directions and exhibit systematic variations in expansion rate or geometry across different directions in space. If our observable universe exists within a region described by Bianchi-type geometry, rather than the perfectly isotropic Friedmann-Lemaitre-Robertson-Walker metric, the cosmic microwave background would exhibit distinctive patterns of temperature and polarization anisotropy that correlate with the geometric structure of space-time itself. Cosmic topology, which describes the global connectivity of space rather than its local geometric properties, could create apparent alignments through the periodic boundary conditions that arise in finite universe models. If the observable universe represents only a portion of a larger space with non-trivial topology, cosmic microwave background patterns might repeat across different regions of the sky, creating correlations between temperature fluctuations that appear to violate statistical isotropy but actually reflect the underlying spatial geometry. Gravitational lensing by large-scale structure introduces correlations between cosmic microwave background fluctuations on different angular scales through the deflection of photon paths by intervening matter distributions. However, lensing effects typically operate on much smaller scales than the quadrupole-octopole alignments and cannot easily explain the observed correlations with ecliptic or galactic reference frames without invoking highly contrived scenarios involving local matter distributions. The hemispherical asymmetry represents another large-scale anomaly in which opposite hemispheres of the cosmic microwave background exhibit systematically different statistical properties, with one hemisphere showing enhanced power in temperature fluctuations compared to the other. This asymmetry appears most prominently at intermediate angular scales and shows some correlation with the axis directions defined by the quadrupole-octopole alignment, suggesting a possible common origin for multiple cosmic microwave background anomalies. Dark energy anisotropy could create preferred directions in cosmic expansion that might manifest as temperature patterns in the cosmic microwave background through the integrated Sachs-Wolf effect or other gravitational phenomena. If dark energy possesses directionally dependent properties, perhaps arising from scalar field dynamics or modifications to general relativity, the resulting anisotropic expansion could imprint distinctive signatures on cosmic microwave background photons during their journey from recombination to the present epoch. Primordial magnetic fields with coherent structure on cosmic scales represent another potential source of statistical anisotropy, though observations severely constrain the strength of such fields during the recombination epoch. Magnetic fields couple to the charged particles in the primordial plasma and could create systematic effects on acoustic oscillations, Thomson scattering, and other physical processes that determine cosmic microwave background temperature and polarization patterns. Statistical significance of the axis of evil depends critically on the choice of statistical measures. Sky masks used to exclude galactic contamination, and corrections for multiple comparisons across different tests and parameter choices. Some studies find that the alignments become less significant when properly accounting for the look elsewhere effect and selection biases, while others maintain that genuine anomalies persist even after conservative statistical corrections. The debate reflects fundamental challenges in interpreting rare events in cosmological datasets. Future observations will test axis alignment hypotheses through improved data quality, extended sky coverage, and complementary probes of large-scale cosmic structure. Next-generation cosmic microwave background experiments will achieve better systematics control and higher sensitivity, enabling more stringent tests of isotropy violations while reducing contamination from instrumental and astrophysical foregrounds. Independent measurements using different experimental approaches will help distinguish genuine cosmological anomalies from systematic effects. Polarization observations provide additional tests of anisotropy hypotheses. Since different physical mechanisms that could generate temperature alignments predict distinct polarization signatures, systematic instrumental effects typically create different patterns in temperature and polarization measurements, while genuine cosmological anisotropy should produce correlated signatures in both observational channels. The combination of temperature and polarization analysis thus offers powerful diagnostics for distinguishing between competing explanations. The question of cosmic isotropy extends beyond academic curiosity to fundamental questions about the nature of space, time, and physical law. Perfect isotropy represents a key assumption underlying modern cosmology and the interpretation of cosmic microwave background observations as probes of universal rather than local physical conditions. Evidence for genuine anisotropy would require substantial revision of cosmological models and might indicate that our observable universe occupies a special or atypical region of a larger, more complex cosmos. The axis of evil continues to align its controversial features across the cosmic microwave background sky, marking directions that may represent either systematic contamination, statistical fluctuations, or genuine evidence for physics beyond the standard cosmological paradigm. These alignments persist in the ancient light that has traveled since recombination, encoding information about the large-scale structure of space-time, the statistical properties of primordial quantum fluctuations, or the systematic limitations of current observational and theoretical frameworks used to interpret humanity's most detailed portrait of the early universe. Cosmic inflation stretches quantum fluctuations to astronomical proportions during the universe's first fraction of a second, creating the nearly scale-invariant spectrum of primordial perturbations that would eventually grow into galaxies, clusters, and the vast cosmic web observed today. This period of exponential expansion, occurring between roughly 10 circumflex 36 and 10 circumflex 32 seconds after the Big Bang, inflates a region smaller than a proton to encompass volumes larger than grapefruit while maintaining the quantum coherence of microscopic fluctuations across macroscopic distances. The inflationary paradigm resolves several conceptual problems that plagued earlier cosmological models. including the horizon problem that questioned how causally disconnected regions of the universe could maintain identical temperatures, and the flatness problem that asked why cosmic geometry appears so precisely balanced between open and closed configurations. Inflation provides elegant solutions by proposing that the observable universe originated from a tiny, causally connected region that underwent exponential expansion, stretching initial quantum fluctuations into the classical perturbations that seeded cosmic structure. The scalar field driving inflation, known generically as the inflaton, must possess specific properties to generate the observed cosmic microwave background temperature fluctuations while avoiding conflicts with other cosmological observations. The inflaton's potential energy density determines the expansion rate during inflation, while the slope of its potential function governs how quickly inflation ends and determines the spectral index that characterizes the scale dependence of primordial perturbations. Most successful inflationary models require fine-tuning of these parameters to match observational constraints. Quantum field theory in curved spacetime provides the theoretical framework for calculating how vacuum fluctuations in the inflaton field generate the density perturbations observed in the cosmic microwave background. The exponential expansion of space during inflation stretches quantum modes beyond the Hubble horizon, where they cease oscillating and become classical perturbations with approximately constant amplitude. Different wavelength modes cross outside the horizon at different times, creating a spectrum of perturbations with slightly different amplitudes. The nearly scale-invariant spectrum predicted by simple inflationary models matches cosmic microwave background observations remarkably well, with the spectral index measuring approximately 0.965, close to the perfectly scale-invariant value of unity, but with a slight tilt toward enhanced power on larger scales. This red tilt provides evidence for the slow-roll evolution of the inflaton field, which must change gradually enough to maintain nearly constant expansion rate throughout the inflationary epoch. Non-Gaussianity in the cosmic microwave background temperature distribution offers potential tests of inflationary physics beyond the simple single-field scenarios that predict purely Gaussian perturbations, multi-field inflation, non-canonical kinetic terms in the inflaton Lagrangian, or interactions between the inflaton and other quantum fields could generate distinctive non-Gaussian signatures that appear as correlations between different multipole moments in the cosmic microwave background power spectrum. Current observations place stringent limits on primordial non-Gaussianity, ruling out many exotic inflationary scenarios. The duration of inflation remains poorly constrained by cosmic microwave background observations, which probe only the final 60 or so E-foldings of exponential expansion that occurred after the largest observable scales crossed outside the horizon. Earlier phases of inflation, if they occurred, would have generated perturbations on scales larger than the observable universe and thus remain forever inaccessible to direct observation. The total duration of inflation depends on unknown physics that operated during the universe's earliest moments. Eternal inflation, proposed as a natural consequence of the quantum nature of scalar fields, suggests that inflation continues indefinitely in most regions of space while ending only in small pockets that become observable universes like our own. In this scenario, the inflationary process never completely terminates, but creates an infinite number of causally disconnected regions with potentially different physical properties. Our observable universe would represent just one bubble in an eternally inflating multiverse. The energy scale of inflation, characterized by the Hubble parameter during the exponential expansion phase, determines the amplitude of tensor perturbations generated by quantum fluctuations in the gravitational field itself. These primordial gravitational waves would create distinctive B-mode polarization patterns in the cosmic microwave background, providing a direct observational probe of quantum gravity physics operating at energies potentially approaching the Planck scale where space-time itself becomes subject to quantum uncertainty. Tensor-to-scalar ratio measurements, which compare the amplitude of gravitational wave perturbations to scalar density perturbations, constrain the energy scale of inflation through the relationship between tensor amplitude and the fourth power of the Hubble parameter during inflation. Current cosmic microwave background observations place upper limits of roughly 0.06 on this ratio, corresponding to inflation occurring at energy scales around 10 circumflex 16 GeV, tantalizingly close to the energy where grand unified theories predict the unification of electromagnetic, weak, and strong nuclear forces. The graceful exit problem asks how inflation transitions smoothly into the radiation-dominated epoch that follows, requiring the inflaton field to decay into ordinary matter and radiation through a process called reheating. This transition must occur in a way that preserves the adiabatic nature of primordial perturbations while avoiding the production of unwanted relics such as magnetic monopoles or other topological defects. The reheating temperature sets the initial conditions for Big Bang nucleosynthesis and determines which particle species achieve thermal equilibrium. Preheating, a violent phase that may precede thermalization during reheating, involves the explosive production of particles through parametric resonance as the inflaton oscillates around the minimum of its potential. This non-thermal process can create highly non-equilibrium conditions with particles occupying high-energy states far from thermal distributions. The details of preheating depend sensitively on the inflaton's interactions with other quantum fields and may generate distinctive observational signatures. Slow-roll parameters characterize the deviation of inflation from exact exponential expansion, measuring how gradually the inflaton field evolves and how quickly the expansion rate changes during the inflationary epoch. These parameters determine both the amplitude and spectral properties of primordial perturbations, with their evolution encoded in the running of the spectral index, a quantity that describes how the spectral tilt varies with wavelength scale. Observations constrain these parameters to be much smaller than unity, confirming the slow-roll approximation. The initial conditions for inflation represent one of the theory's most mysterious aspects, requiring the universe to begin in a special state with the inflaton field displaced from its potential minimum and possessing nearly uniform energy density across regions that had no prior causal contact. Some models invoke quantum cosmology or eternal inflation to explain these initial conditions, while others simply postulate them as boundary conditions for the observable universe's evolution. String theory motivates various inflationary scenarios through the dynamics of extra-dimensional geometry, with inflation driven by the motion of branes in higher dimensional spaces or by moduli fields that determine the size and shape of compactified dimensions. These string-motivated models often predict specific relationships between cosmological observables and may generate distinctive signatures such as cosmic superstrings that could appear in cosmic microwave background observations. Loop quantum cosmology, an approach based on the quantization of general relativity using techniques from loop quantum gravity, suggests that inflation may be preceded by a contracting phase that bounces into expansion when quantum effects become dominant at extremely high densities. This quantum bounce could replace the initial singularity of classical cosmology while naturally providing the initial conditions required for successful inflation. Modified gravity theories offer alternatives to inflation that attempt to explain cosmic microwave background observations through modifications to Einstein's general relativity rather than the introduction of new scalar fields. These approaches typically involve higher derivative terms in the gravitational action or extra-dimensional effects that alter the early universe's expansion dynamics. However, most modified gravity alternatives face significant theoretical and observational challenges. The multiverse implications of inflation suggest that if the mechanism operated in our universe, it likely continues indefinitely in other regions of space, creating an infinite ensemble of causally disconnected observable universes with potentially different physical parameters. This possibility raises profound questions about the predictive power of physical theories and the anthropic reasoning used to explain observed parameter values through selection effects. Observational tests of inflation extend beyond cosmic microwave background measurements to include constraints from Big Bang nucleosynthesis, large-scale structure formation, and gravitational wave observations. The combination of different observational probes provides increasingly stringent tests of inflationary predictions while constraining the space of viable models. Future observations will either confirm inflation's detailed predictions or reveal deviations that point toward alternative theories. The inflaton field, if it exists, continues to influence cosmic evolution long after the end of inflation through its potential role in dark energy. Quintessence, or other late-time phenomena. Some models propose that the same field responsible for primordial inflation might also drive the currently observed acceleration of cosmic expansion, creating connections between the earliest and latest epochs of cosmic history. These scenarios predict specific relationships between early and late-time cosmological parameters. Inflation's theoretical fingerprints remain embedded in the cosmic microwave background's temperature and polarization patterns, encoding information about quantum field dynamics operating under the most extreme physical conditions imaginable. The detection of primordial B-mode polarization would provide direct evidence for gravitational waves generated during inflation, confirming both the inflationary paradigm and the quantum nature of gravity itself. Even without this smoking gun signature, the cosmic microwave background's statistical properties continue to constrain inflationary physics with ever-increasing precision. The inflationary universe stretches its quantum legacy across cosmic time, imprinting the signatures of microscopic uncertainty onto the largest observable structures while raising fundamental questions about the nature of physical law. The uniqueness of our cosmic environment, and humanity's place within a potentially infinite multiverse of causally disconnected realities that may never be directly observable, but whose existence follows from the same quantum principles that govern laboratory physics and create the patterns detected in ancient light from the cosmic microwave background. B-mode polarization hunting represents modern cosmology's most challenging observational quest, seeking to detect the faint rotational patterns in ancient light that would provide direct evidence for gravitational waves generated during cosmic inflation and probe quantum gravity physics at energy scales approaching the fundamental Planck limit. These elusive signals hide beneath layers of contamination from galactic dust, synchrotron radiation, and gravitational lensing effects, requiring instruments of extraordinary sensitivity and sophisticated data analysis techniques to separate primordial signatures from astrophysical foregrounds. The primordial B-mode signal, if it exists, would measure less than 100 nanokelvin in equivalent temperature units, fluctuations so small they represent less than 1 part in 100 million of the cosmic microwave background's average temperature. Detecting such subtle patterns demands cooling detector systems to within millikelvin of absolute zero, deploying thousands of superconducting sensors, and achieving systematic error control at levels that challenge the fundamental limits of experimental physics. The technological requirements push beyond current capabilities and motivate the development of revolutionary approaches to precision measurement. Tensor perturbations, the gravitational wave analogues of the scalar density perturbations that create temperature fluctuations, naturally generate B-mode polarization through their effects on photon geodesics in curved spacetime, unlike scalar perturbations, which can only produce curl-free E-mode polarization patterns. Tensor modes exhibit intrinsic handedness that creates the rotational B-mode signatures. The amplitude of this primordial B-mode signal depends directly on the energy scale of inflation, providing a unique observational window into processes that occurred during the universe's first 10 circumflex, 32 seconds. Ground-based experiments deploy increasingly sophisticated arrays of detectors at carefully chosen high-altitude sites where atmospheric water vapor remains minimal and weather conditions provide stable observing conditions for extended periods. The South Pole offers ideal conditions with 6-month observing seasons, extremely low water vapor content, and negligible ground pickup from surrounding terrain. The Atacama Desert in Chile provides complementary advantages with higher elevation, exceptional atmospheric transparency, and access to larger regions of the sky. The BICEP, Background Imaging of Cosmic Extragalactic Polarization program, represents the most focused search for primordial B modes, deploying successive generations of increasingly sensitive telescopes at the South Pole that target specific patches of sky with minimal galactic contamination. BICEP-2's 2014 announcement of a potential B-mode detection generated tremendous excitement before subsequent analysis revealed that galactic dust emission could account for the observed signals. This experience highlighted both the promise and the challenges of B-mode detection in the presence of foreground contamination, galactic dust grains, aligned by magnetic fields within the Milky Way, emit polarized thermal radiation that mimics the B-mode patterns expected from primordial gravitational waves. The dust emission increases toward higher frequencies where the cosmic microwave background signal peaks, creating maximum contamination precisely where the cosmological signal achieves its highest signal-to-noise ratio. Separating these components requires observations across multiple frequency bands combined with sophisticated statistical analysis techniques. Synchrotron emission from relativistic electrons spiraling in galactic magnetic fields provides another source of polarized contamination that exhibits intrinsic B-mode structure at the low frequencies where cosmic microwave background experiments often operate. The synchrotron spectrum decreases toward higher frequencies with a power law index that varies across the sky, complicating component separation efforts and requiring detailed modeling of galactic magnetic field structure and cosmic ray propagation. Instrumental systematics represent perhaps the greatest challenge in B-mode detection, as any asymmetry in detector response, beam patterns, or calibration accuracy can generate spurious polarization signals that mimic cosmological signatures. Temperature to polarization leakage, where small errors in beam measurements create artificial polarization from the much larger temperature fluctuations, poses particular difficulties. Controlling these systematic effects requires unprecedented instrument characterization and calibration procedures. Cross-linking observational strategies, where the same patch of sky is observed from multiple orientations as the telescope rotates, help distinguish genuine polarization signals from instrumental artifacts that remain fixed relative to the telescope's coordinate system. Genuine sky polarization rotates with the telescope orientation, while systematic errors typically maintain fixed patterns. This approach requires extremely stable instrumental properties and careful attention to thermal variations and mechanical flexure. Atmospheric emission, despite the choice of exceptionally dry observing sites, introduces time-variable contamination that couples to instrumental and scanning systematics in complex ways. Precipitable water vapor as low as 0. 5 mm still generates measurable emission at millimeter wavelengths, while temperature fluctuations in the atmosphere create gain variations that must be calibrated in real time. Advanced atmospheric monitoring systems track these variations, while sophisticated data analysis techniques remove their effects. Component separation algorithms employ the different frequency dependencies of cosmological and astrophysical signals to reconstruct clean cosmic microwave background maps from multi-frequency observations. Maximum likelihood methods optimally weight observations based on noise properties and known signal characteristics, while independent component analysis techniques identify mixing patterns between different physical processes. These methods require accurate knowledge of foreground spectral properties across the observing bands. Statistical analysis of B-mode measurements requires sophisticated treatment of noise properties, sky cuts, and systematic uncertainties that can bias power spectrum estimates. The B-mode power spectrum typically exhibits lower signal-to-noise ratios than E-mode or temperature measurements, making it more susceptible to systematic contamination and analysis errors. Monte Carlo simulations test analysis pipelines while providing realistic estimates of statistical uncertainties. Delensing techniques attempt to remove the B-mode polarization created by gravitational lensing of primordial E-mode patterns, potentially improving sensitivity to primordial B-modes by factors of several. These methods use temperature and E-mode measurements to reconstruct the lensing potential that created the secondary B-modes, then subtract the predicted lensing contribution from the observed B-mode maps. Successful delensing requires high-fidelity lensing reconstruction and careful treatment of noise correlations. Future experiments will achieve the sensitivity required to detect primordial B-modes at the levels predicted by viable inflationary models, potentially reaching tensor to scalar ratios as low as 10 circumflex 3 through the combination of improved detector technology, larger arrays, and better foreground control. Space-based missions avoid atmospheric contamination while achieving full sky coverage, though they face greater challenges in cooling systems and systematic error characterization. CMBS-4, a proposed next-generation ground-based experiment, would deploy hundreds of thousands of superconducting detectors across multiple sites to map cosmic microwave background polarization with unprecedented precision. The experiment aims to achieve definitive measurements or stringent upper limits on primordial B-modes while simultaneously constraining neutrino masses, dark energy properties, and other fundamental parameters through complementary observations of temperature and E-mode polarization. Balloon-borne experiments provide intermediate steps towards space-based observations while testing new technologies and analysis methods in controlled environments. These missions achieve partial sky coverage from stratospheric altitudes where atmospheric emission becomes negligible, providing clean measurements across multiple frequency bands. Successive flights allow instrument improvements and cross-validation of results from different observational platforms. The theoretical interpretation of B-mode measurements extends beyond simple amplitude constraints to include detailed analysis of the multipole dependence, which encodes information about the inflationary epoch's duration, energy scale, and physical processes. Different inflationary models predict subtle differences in the B-mode angular power spectrum that may be detectable with sufficient observational precision. These measurements could distinguish between competing theories of the early universe. Primordial gravitational wave backgrounds continue to propagate through space at light speed, carrying information about quantum gravity phenomena that occurred during cosmic inflation while interacting weakly with matter and electromagnetic radiation. The B-mode polarization patterns they create in the cosmic microwave background represent humanity's best hope for directly observing these relics of quantum space-time, providing experimental access to physics that operates at energy scales far beyond terrestrial particle accelerators and potentially confirming the quantum nature of gravity itself through precision measurements of ancient light. The multiverse hypothesis emerges from cosmic inflation theory as an almost inevitable consequence of eternal inflation, suggesting that our observable universe represents just one bubble in an infinite foam of causally disconnected regions where physical laws, fundamental constants, and even the dimensionality of space itself might vary in ways that challenge conventional notions of uniqueness and universal physical principles. If inflation occurred in our cosmic neighborhood, quantum fluctuations ensure that it continues indefinitely in most regions of space, ending only in rare pockets that become observable universes with finite lifespans. Collision signatures between bubble universes could potentially leave observable traces in the cosmic microwave background if our universe encountered another expanding bubble during its early expansion phase, creating distinctive circular temperature and polarization patterns that differ qualitatively from the Gaussian fluctuations expected from single-universe inflation. Such collisions would produce correlated hot and cold regions with specific geometric relationships determined by the relative velocities, sizes, and internal properties of the colliding bubbles. The landscape of string theory provides a theoretical framework for understanding how different bubble universes might possess different physical properties through the stabilization of moduli fields in distinct vacuum states corresponding to different compactifications of extra dimensions. Each vacuum state would exhibit different values of fundamental parameters such as particle masses, coupling constants, and cosmological constants, creating a vast ensemble of possible universes with varying degrees of hospitability to structure formation and biological evolution. Anthropic reasoning attempts to explain the observed values of fundamental constants through selection, effects that bias observations toward parameter combinations compatible with the existence of observers, rather than requiring these values to follow from deeper physical principles. In a multiverse context, most regions would possess parameter values incompatible with star formation, planet formation, or the complex chemistry required for life, making observer selection effects statistically inevitable rather than philosophically problematic. The cosmological constant problem, which asks why the observed dark energy density is so much smaller than naive quantum field theory predictions, finds potential resolution in multiverse scenarios where different regions exhibit different vacuum energy densities. Most universes would possess cosmological constants so large that they would either recollapse immediately or expand so rapidly that structure formation becomes impossible, leaving only a small fraction with values compatible with galaxy formation and observer evolution. Eternal inflation creates an infinite number of observable universes through the stochastic nature of quantum field dynamics, with different regions exiting inflation at different times and evolving according to slightly different initial conditions and physical parameters. The measure problem asks how to assign probabilities to different outcomes in such an infinite ensemble. Since standard probability theory breaks down when dealing with infinite sets of events that each occur infinitely often, observable consequences of the multiverse remain extremely limited because causal horizons prevent direct communication between different bubble universes, restricting potential evidence to subtle statistical anomalies in the cosmic microwave background or other observational signatures that might preserve traces of pre-inflation physics or inter-universe interactions. Most multiverse effects would be unobservable in principle, raising questions about the scientific status of theories that make untestable predictions. The string landscape contains an estimated 10 circumflex 500 or more distinct vacuum states, each corresponding to a different way of compactifying the 6 extra dimensions predicted by string theory down to the 4 dimensions of ordinary space-time. This enormous number of possibilities, far exceeding the number of atoms in the observable universe, suggests that almost any combination of physical parameters might be realized somewhere in the multiverse, making specific predictions impossible without additional theoretical constraints. False vacuum decay represents one mechanism through which bubble universes might form, occurring when metastable vacuum states tunnel quantum mechanically into lower energy configurations and create expanding regions of true vacuum surrounded by walls of false vacuum. The dynamics of these phase transitions determine the internal properties of the resulting bubbles while potentially creating observable signatures at the boundaries between different vacuum domains. Cosmological natural selection, proposed by Lee Smolin, suggests that universes capable of producing black holes through stellar evolution might generate more descendant universes through processes that occur beyond black hole event horizons, creating evolutionary pressure toward parameter values that maximize black hole production. This mechanism could explain the apparent fine-tuning of physical constants without requiring anthropic reasoning or observer selection effects. The holographic principle, derived from black hole thermodynamics and string theory, suggests that the information content of any volume of space can be encoded on its two-dimensional boundary, raising profound questions about the fundamental nature of space, time, and physical reality that extend to multiverse scenarios. If our three-dimensional universe represents a holographic projection of information stored on a distant two-dimensional surface, similar principles might apply to other universes in the multiverse ensemble. Quantum mechanics in multiverse contexts requires careful interpretation of concepts such as measurement, wave function collapse, and the role of observers when multiple parallel universes might exist simultaneously in quantum superposition states. The many worlds interpretation naturally accommodates multiverse scenarios by treating each bubble universe as one branch of a vast quantum superposition, while other interpretations face greater conceptual challenges. Mathematical universes, as proposed in Max Tegmark's ultimate ensemble theory, suggest that all mathematically consistent structures exist as physical realities, making our universe just one particular mathematical object among infinitely many possibilities. This radical proposal eliminates the distinction between mathematical and physical existence, while providing a framework for understanding why we observe the specific mathematical relationships that appear to govern natural phenomena. Observational searches for multiverse signatures focus on statistical anomalies in cosmic microwave background temperature and polarization maps that might preserve evidence of pre-inflationary physics or interactions between different vacuum domains. These searches require sophisticated pattern recognition algorithms and careful statistical analysis to distinguish genuine anomalies from random fluctuations, instrumental systematics, or data analysis artifacts. Vacuum metastability calculations suggest that the Higgs field in our universe might exist in a metastable state that could decay into a lower energy configuration over cosmological timescales, potentially triggering a catastrophic phase transition that would destroy all current forms of matter and energy. The timescale for such decay depends sensitively on the precise values of particle physics parameters and might vary dramatically across different regions of the multiverse. Cognitive bias concerns arise in multiverse discussions because humans naturally seek explanations that make their existence seem special or meaningful, potentially leading to acceptance of theories that appear to explain anthropic coincidences regardless of their empirical support or predictive power. Scientific evaluation of multiverse hypotheses requires careful separation of aesthetic preferences from observational evidence and theoretical consistency. The inflationary multiverse paradigm suggests that space extends infinitely beyond our observable horizon, containing infinitely many regions identical to our own, as well as infinitely many variations with different histories, outcomes, and physical properties. In such a scenario, every possible sequence of events that remains consistent with physical law occurs infinitely often across the infinite ensemble of causally disconnected observable volumes. Experimental tests of multiverse theories remain largely indirect, focusing on precision measurements of fundamental constants, searches for anomalous patterns in cosmic microwave background observations, and theoretical consistency checks that might rule out specific multiverse scenarios without directly observing other universes. The combination of these approaches provides the strongest available constraints on multiverse hypotheses within the bounds of scientific methodology. The multiverse concept continues to challenge conventional notions of cosmic uniqueness and universal physical law, suggesting that our observable universe might represent just one temporary fluctuation in an eternal process of inflation that creates infinitely many causally disconnected regions with potentially different physical properties, fundamental constants, and evolutionary histories. Whether such ideas can ever achieve empirical confirmation or must remain permanently speculative continues to generate intense debate among physicists and philosophers investigating the deepest questions about existence, observation, and the nature of physical reality itself. Machine learning algorithms analyze cosmic microwave background data with inhuman patience and precision, detecting subtle correlations and statistical patterns that remain invisible to traditional analysis methods, while processing datasets containing billions of temperature and polarization measurements across multiple frequency bands. These artificial intelligence systems operate without the cognitive biases and pattern recognition limitations that constrain human perception, potentially uncovering evidence for exotic physics, systematic errors, or statistical anomalies that might otherwise remain hidden within the complexity of modern cosmological observations. Neural networks trained on simulated cosmic microwave background maps learn to identify features associated with different physical processes, developing internal representations that capture the statistical relationships between inflationary parameters, reionization histories, and observational signatures without explicit programming of the underlying physics. Deep learning architectures with millions of adjustable parameters can simultaneously model foreground contamination, instrumental systematics, and cosmological signals while automatically discovering optimal feature combinations for parameter estimation. Convolutional neural networks exploit the spatial structure of cosmic microwave background maps by using filter operations that detect localized patterns at different angular scales, mimicking the hierarchical processing performed by biological visual systems while achieving superhuman performance in pattern recognition tasks. These networks learn translation-invariant features that remain consistent across different sky locations while adapting to the statistical properties of cosmic microwave background fluctuations and their associated noise characteristics. Unsupervised learning techniques identify hidden structures in cosmic microwave background data without prior knowledge of the expected signals, using algorithms such as independent component analysis, clustering methods, and dimensionality reduction to discover emergent patterns that might correspond to unknown physical processes or previously unrecognized systematic effects. These approaches complement traditional model-fitting procedures by exploring the data space without strong theoretical assumptions. Principal component analysis decomposes cosmic microwave background maps into orthogonal modes ranked by their contribution to the total variance, potentially isolating components associated with primordial fluctuations. Galactic foregrounds, instrumental noise, or exotic signals that deviate from standard cosmological expectations. The principal components often reveal unexpected correlations between different sky regions or frequency bands that suggest new physical processes or analysis challenges. Gaussian process regression provides probabilistic frameworks for cosmic microwave background analysis that naturally incorporate uncertainty quantification while interpolating between sparse measurements and extrapolating to unobserved regions of parameter space. These methods excel at modeling smooth functions with complex covariant structures, making them particularly suitable for component separation problems where different astrophysical processes exhibit distinct but overlapping frequency dependencies. Bayesian neural networks combine the pattern recognition capabilities of deep learning with rigorous uncertainty quantification, providing probabilistic predictions that account for both statistical noise and systematic uncertainties in cosmic microwave background parameter estimation. These hybrid approaches use Monte Carlo dropout, variational inference, or ensemble methods to sample from posterior distributions over network parameters while propagating uncertainties through complex nonlinear transformations. Generative adversarial networks learn to synthesize realistic cosmic microwave background realizations by training competing neural networks in a minimax game where generators create fake maps while discriminators attempt to identify synthetic data. Successfully trained generators capture the statistical properties of cosmic microwave background fluctuations and can produce unlimited quantities of realistic simulations for testing analysis pipelines and validating theoretical predictions. Transfer learning adapts neural networks trained on large datasets to related problems with limited training data, potentially leveraging simulations from different cosmological models or observational datasets from different experiments. This approach accelerates the development of analysis tools for new missions while reducing the computational requirements for training complex architectures from scratch. Attention mechanisms, borrowed from natural language processing. Identify the most relevant regions of cosmic microwave background maps for specific analysis tasks, automatically focusing computational resources on features that contribute most strongly to parameter constraints or anomaly detection. These mechanisms provide interpretability by highlighting which spatial locations or frequency channels drive particular conclusions. Ensemble methods combine predictions from multiple machine learning models to improve robustness and reduce overfitting, using techniques such as random forests, gradient boosting, or deep ensembles to aggregate diverse approaches to cosmic microwave background analysis. The combination of different algorithms often achieves superior performance compared to individual methods while providing more reliable uncertainty estimates. Anomaly detection algorithms specifically target unusual patterns in cosmic microwave background data that might indicate systematic errors, instrumental artifacts, or genuinely anomalous cosmological signals. These methods learn the statistical properties of normal cosmic microwave background fluctuations and identify regions or features that deviate significantly from expected behavior, potentially revealing evidence for exotic physics or data quality issues. Reinforcement learning optimizes observing strategies and data analysis procedures by treating cosmic microwave background experiments as sequential decision problems where algorithms learn to maximize scientific return through interaction with simulated environments. These approaches can optimize telescope pointing strategies, frequency channel selection, or analysis pipeline parameters while adapting to changing instrumental conditions. Interpretability techniques attempt to understand how machine learning models make decisions about cosmic microwave background data, using methods such as gradient-based attribution, layer-wise relevance propagation, or surrogate model analysis to identify which input features most strongly influence model predictions. This interpretability is crucial for building scientific confidence in machine learning results and identifying potential failure modes. Feature engineering for cosmic microwave background analysis involves the construction of physically meaningful input representations that capture relevant statistical properties while remaining robust to noise and systematic effects. Successful features might include spherical harmonic coefficients, wavelet transforms, topological descriptors, or physically motivated summary statistics that compress high-dimensional map data into manageable representations. Cross-validation procedures ensure that machine learning models generalize beyond their training data by testing performance on held-out cosmic microwave background simulations or observational datasets. These validation schemes must account for the unique challenges of cosmological data analysis, including correlated noise, incomplete sky coverage, and the limited availability of independent datasets for testing. Hyperparameter optimization tunes the architecture and training procedures of machine learning models for optimal performance on cosmic microwave background analysis tasks, using techniques such as grid search, random search, or Bayesian optimization to explore the space of possible model configurations. This optimization process often reveals unexpected parameter combinations that achieve superior performance through mechanisms that remain poorly understood. Computational efficiency considerations become critical when applying machine learning to cosmic microwave background analysis. As modern datasets contain billions of pixels observed across multiple frequency bands and time periods, efficient algorithms must balance accuracy against computational cost while exploiting parallel processing capabilities and specialized hardware such as graphics processing units designed for machine learning applications. Systematic error mitigation represents one of the most promising applications of machine learning to cosmic microwave background science, as algorithms can potentially identify and correct for instrumental artifacts that vary in complex ways across time, frequency, and spatial location. Machine learning models can learn the relationships between instrumental telemetry, environmental conditions, and data quality metrics to predict and remove systematic contamination. Future cosmic microwave background experiments will generate data sets of unprecedented size and complexity, containing petabytes of time-ordered data from hundreds of thousands of detectors operating simultaneously across multiple frequency bands. Machine learning algorithms will become essential tools for managing this data volume while extracting maximum scientific information from observations that push the boundaries of instrumental sensitivity and systematic error control. The application of artificial intelligence to cosmic microwave background analysis represents a new frontier where computational pattern recognition meets fundamental physics, potentially revealing hidden structures in ancient light that preserve information about quantum gravity. Extra dimensions, or other exotic phenomena that operated during the universe's earliest moments. These algorithms continue to evolve and improve, developing increasingly sophisticated approaches to the challenge of extracting cosmological truth from noisy, contaminated observations of the most distant electromagnetic radiation accessible to human measurement. The boundaries of observable truth extend only as far as the cosmic microwave background allows, marking the earliest epoch from which electromagnetic radiation can reach present-day detectors and defining fundamental limits on humanity's ability to probe the universe's initial conditions through direct observation. Beyond the surface of last scattering lies a cosmic dark age where photons remained coupled to matter in an opaque plasma, rendering that earlier era permanently invisible to conventional astronomical techniques regardless of future technological advances. Information. Theoretical limits constrain the amount of cosmological knowledge that can be extracted from cosmic microwave background observations, as the finite number of independent modes on the observable sky places upper bounds on parameter estimation precision that no amount of instrumental improvement can circumvent. The cosmic variance limit represents an irreducible uncertainty arising from the statistical nature of primordial fluctuations, ensuring that some aspects of early universe physics will remain forever uncertain. Noise barriers establish practical limits on cosmic microwave background measurements through a combination of instrumental thermal noise, photon shot noise, and systematic errors that become increasingly difficult to control as sensitivity requirements approach fundamental physical limits. Detector systems operating at millikelvin temperatures already approach the quantum limit where further cooling provides diminishing returns, while systematic error control requires unprecedented stability and calibration accuracy. Foreground contamination presents astrophysical limits on cosmic microwave background science, as galactic dust emission, synchrotron radiation, and other contaminants can mimic or mask the primordial signals of greatest cosmological interest. Component separation techniques can partially remove these foregrounds, but residual contamination ultimately limits the precision of parameter measurements and the detectability of exotic signals such as primordial B-mode polarization. The cosmic microwave background encodes information about physical processes that occurred during a limited time window around recombination, constraining observations to probe conditions when the universe was roughly 380,000 years old. Earlier epochs remain accessible only through their influence on the conditions at recombination, creating indirect connections that become increasingly tenuous for phenomena that occurred during the universe's first microseconds. Model dependence affects cosmic microwave background interpretation because extracting physical parameters requires assuming specific theoretical frameworks that may not capture all relevant physics. The standard lambda CDM cosmological model provides an excellent fit to current observations, but extensions or alternatives could yield different parameter values and physical conclusions. The cosmic microwave background alone cannot definitively distinguish between many competing theoretical scenarios. Degeneracies between cosmological parameters limit the constraining power of cosmic microwave background observations, as multiple combinations of physical quantities can produce nearly identical temperature and polarization patterns. Parameter degeneracies can be partially broken by combining cosmic microwave background data with other observational probes. But some fundamental ambiguities may persist regardless of data quality improvements. The finite resolution of cosmic microwave background experiments restricts observations to angular scales larger than the instrumental beam size, typically several arcminutes for ground-based telescopes and tens of arcminutes for satellite missions. Smaller scale physics becomes increasingly difficult to probe as beam dilution and noise increase, potentially hiding signatures of exotic processes that operate on scales approaching the cosmic microwave background's intrinsic damping length. Statistical limitations arise from the finite number of observable modes in cosmic microwave background temperature and polarization maps, particularly on large angular scales where cosmic variance dominates measurement uncertainties. The quadrupole and octupole moments, which probe the largest physical scales, each contain only a few independent measurements, making statistical conclusions about large-scale anomalies inherently uncertain. Systematic error flaws represent the practical limits of current cosmic microwave background experiments, beyond which further improvements in statistical sensitivity cannot improve parameter constraints. These flaws arise from imperfect knowledge of instrumental properties, atmospheric contamination, foreground removal residuals, and other effects that remain after all known corrections have been applied. Future experiments must address these systematic limitations to achieve their scientific goals. The Rayonization epoch creates additional complications for cosmic microwave background interpretation by introducing secondary scattering that modifies the primordial polarization patterns while adding new sources of uncertainty about the intergalactic medium's ionization history. The optical depth to rayonization remains poorly constrained, creating parameter degeneracies that limit the precision of other cosmological measurements. Nonlinear physics during structure formation affects cosmic microwave background observations through gravitational lensing by evolved matter distributions that departed from the linear regime billions of years after recombination. While lensing effects can be partially corrected through delensing procedures, residual contamination may limit the detectability of primordial signals, particularly B-mode polarization from gravitational waves. Instrumental polarization presents ongoing challenges for cosmic microwave background experiments because any asymmetry in detector response, optical properties, or calibration procedures can generate spurious polarization signals that mimic cosmological signatures. Temperature to polarization leakage remains particularly problematic because temperature fluctuations are roughly 100 times larger than polarization signals, making even tiny systematic effects potentially significant. The finite lifetime of cosmic microwave background experiments limits the total observation time available for improving statistical precision, while instrumental aging and environmental changes introduce time-dependent systematic effects that complicate long-term observations. Space-based missions face additional constraints from consumable coolant supplies and component degradation in the harsh space environment. Theoretical uncertainties affect cosmic microwave background predictions through incomplete knowledge of recombination physics, helium ionization details, and other atomic processes that occurred during the transition from opacity to transparency. While these uncertainties are small compared to current observational errors, they may become limiting factors for future precision measurements that approach percent-level accuracy. The anthropic principle introduces philosophical complications for cosmic microwave background interpretation by suggesting that observed parameter values might reflect selection effects rather than fundamental physical principles. In multiverse scenarios, most regions would possess parameters incompatible with structure formation and observer evolution, making it unclear whether cosmic microwave background observations probe universal physics or just the local conditions compatible with our existence. Computational limitations constrain the complexity of theoretical models that can be compared with cosmic microwave background data as full numerical simulations of recombination. Reionization and structure formation require enormous computational resources that may not capture all relevant physics. Approximations and simplifications introduce theoretical uncertainties that propagate into parameter estimates and physical conclusions. Confirmation bias risks affecting cosmic microwave background science when researchers unconsciously favor interpretations that support preferred theoretical frameworks or expected results. The subtlety of systematic effects and the complexity of data analysis procedures create opportunities for bias to influence conclusions, making independent verification and blind analysis procedures essential for reliable results. The cosmic microwave background represents humanity's deepest direct observational probe of the universe's history, yet it illuminates only a brief moment in cosmic evolution while leaving earlier epochs shrouded in electromagnetic darkness. Future advances in gravitational wave astronomy, neutrino detection, and other non-photonic probes may eventually pierce this observational barrier. But the cosmic microwave background will likely remain our most detailed portrait of the universe's transition from opacity to transparency, preserving in its ancient light both the ultimate achievements and fundamental limitations of electromagnetic astronomy in probing the deepest questions about existence itself. Silence pervades the spaces between cosmic microwave background photons as they stream through the vast emptiness of intergalactic space, carrying their ancient messages across billions of light-years while encountering almost nothing that might alter their primordial polarization states or temperature signatures. The universe has become largely transparent to these relics of recombination, allowing them to propagate essentially unimpeded from the surface of last scattering to present-day detectors that measure their arrival with exquisite precision. The cosmic microwave background continues its patient broadcast, regardless of whether conscious observers exist to detect its signals, transmitting information about primordial quantum fluctuations, acoustic oscillations, and gravitational lensing effects with mechanical persistence across cosmic time. The photons carry no awareness of their significance to cosmology, no recognition of the profound questions their statistical properties might resolve, only the electromagnetic field configurations impressed upon them during their final interactions with free electrons nearly 14 billion years ago. Radio telescopes across Earth point silently toward different patches of sky, their dish surfaces collecting cosmic microwave background photons that began their journeys when the universe was roughly 3% of its current age. The instruments operate with mechanical precision, cooling their detectors to temperatures approaching absolute zero, while tracking the apparent motion of celestial coordinates across the rotating sky. Most cosmic microwave background photons pass through these telescopes without interaction, continuing their journeys toward other destinations in the expanding universe. The statistical properties of cosmic microwave background temperature fluctuations encode information about physical processes that occurred during epochs when the universe bore no resemblance to its current structure, containing neither stars nor galaxies nor planets nor any of the familiar objects that populate contemporary astronomy. The ancient light preserves evidence of a cosmos dominated by radiation rather than matter, where the entire observable universe could have fit within the present-day solar system and where quantum mechanical uncertainty governed the initial conditions from which all subsequent complexity would emerge. Each cosmic microwave background photon detected represents one member of an enormous statistical ensemble, contributing infinitesimally to the maps and power spectra that reveal the universe's large-scale properties, while carrying only a tiny fraction of the total information content. Individual photons provide no cosmological knowledge, becoming meaningful only when combined with billions of their companions through sophisticated statistical analysis that extracts signals from noise through the patient accumulation of data across years of continuous observation. The polarization patterns frozen into the cosmic microwave background encode the final moments of Thomson scattering between photons and free electrons, preserving information about velocity fields, magnetic influences, and gravitational perturbations that existed during recombination. These patterns remain unchanged as the photons traverse cosmic distances, maintaining their orientations relative to the local reference frame while the universe expands around them and new structures form from the gravitational collapse of dark matter and ordinary matter. Gravitational lensing by dark matter structures subtly deflects cosmic microwave background photons from their original trajectories, creating correlations between temperature fluctuations on different angular scales while distorting the primordial polarization patterns through the differential deflection of neighboring light rays. The lensing effect accumulates gradually as photons encounter successive gravitational perturbations during their journey, creating a cumulative signal that encodes information about the entire matter distribution along the line of sight. The cosmic microwave background fills every cubic centimeter of space with roughly 400 ancient photons, creating a uniform bath of electromagnetic radiation that bathes all matter in the present-day universe. These photons interact only weakly with contemporary astrophysical processes, having energies too low to ionize atoms or drive significant chemical reactions. Yet they represent the most abundant form of electromagnetic radiation in the cosmos by number density, if not by energy content. Future cosmic evolution will gradually redshift the cosmic microwave background to longer wavelengths as the universe continues expanding, cooling the radiation toward ever lower temperatures while preserving its blackbody spectral form and statistical properties. In the far future, when stellar evolution has ended and galaxies have dispersed through cosmic expansion, the cosmic microwave background will persist as one of the last remaining traces of the universe's hot, dense initial state. The information content of the cosmic microwave background approaches its maximum extractable value as observational precision reaches fundamental limits imposed by cosmic variance, instrumental noise, and systematic uncertainties that cannot be eliminated through technological improvements alone. Future experiments may achieve marginal improvements in parameter constraints, but the primary cosmological lessons encoded in the ancient light have likely been learned through decades of increasingly sophisticated observation and analysis. Quantum mechanics governs both the initial generation of cosmic microwave background fluctuations through vacuum fluctuations during inflation and their final detection through photoelectric interactions in superconducting sensors cooled to millikelvin temperatures. The cosmic microwave background thus connects quantum physics operating on microscopic scales to cosmological observations that span the observable universe, demonstrating the unity of physical law across vast ranges of energy, distance, and time. The surface of last scattering represents the most distant electromagnetic source accessible to astronomical observation, marking the boundary beyond which the universe becomes opaque to photons and electromagnetic astronomy reaches its fundamental limit. This surface exists not as a physical boundary, but as the three-dimensional locus of points from which cosmic microwave background photons last scattered from free electrons before traveling directly to present-day observers. Cosmic microwave background observations have achieved their primary scientific objectives through the measurement of fundamental cosmological parameters with precision sufficient to establish the standard lambda CDM model and constrain alternative theories. The major discoveries: confirmation of the hot Big Bang model, evidence for cosmic inflation, constraints on neutrino masses and dark energy properties represent permanent additions to scientific knowledge that will persist regardless of future observational developments. The ancient photons continue their journeys beyond Earth toward destinations elsewhere in the expanding universe, carrying the same statistical information about primordial fluctuations, acoustic oscillations, and gravitational lensing effects that enabled humanity's cosmological discoveries. Other civilizations, if they exist and possess sufficiently advanced technology, might detect these same signals and reach similar conclusions about cosmic history, initial conditions, and fundamental physics. The cosmic microwave background approaches asymptotic scientific maturity as technological limits constrain future improvements in observational precision, while theoretical understanding achieves completeness in describing the physical processes that created and modified the primordial electromagnetic signals. Remaining questions focus primarily on exotic signatures, primordial B-mode polarization, non-Gaussianity, statistical anomalies that require extraordinary observational sensitivity and may ultimately prove undetectable. Instrumental development for cosmic microwave background science has pushed measurement technology to fundamental physical limits, driving advances in cryogenics, superconducting devices, and precision calibration that benefit other fields of experimental physics. The requirement for detecting signals at the level of tens of nanokelvin has necessitated innovations in noise reduction, systematic error control, and statistical analysis that represent permanent contributions to experimental science. The mathematical frameworks developed for cosmic microwave background analysis, spherical harmonic decomposition, optimal filtering, component separation, parameter estimation, provide tools that extend far beyond cosmology to applications in geophysics, climate science, medical imaging, and other fields requiring the extraction of weak signals from noisy, contaminated data sets. These methods represent lasting intellectual achievements that will persist regardless of future cosmological developments. The silence between stars deepens as cosmic expansion continues, increasing the mean separation between galaxies while cooling the cosmic microwave background toward temperatures that will eventually fall below the threshold of practical detection. The universe moves gradually toward a state of maximum entropy where information becomes increasingly difficult to extract, and the cosmic microwave background fades into the quantum noise that underlies all physical measurement, carrying its ancient testimony toward a future where consciousness itself may no longer exist to contemplate the meaning of existence. The cosmic microwave background whispers its final secrets into instruments that listen with electronic patience, detecting the last measurable traces of primordial light as it fades toward invisibility in the expanding cosmos. Each photon carries its quantum payload across distances that dwarf human comprehension, maintaining perfect fidelity to the statistical patterns impressed during recombination while the universe ages around them through stellar birth and death, galactic collision and dispersion, and the slow decay of all organized structure. The ancient radiation streams through space with mechanical indifference to the profound questions it helps resolve, carrying information about quantum gravity, extra dimensions, and the ultimate nature of space and time in electromagnetic field configurations that preserve their message across cosmic epochs. The photons know nothing of their significance to conscious observers who develop the mathematics to decode their statistical properties and extract cosmological truth from noise. Silence settles over the cosmic microwave background experiments as they complete their observations and power down their cryogenic systems, having achieved their scientific objectives through decades of patient measurement and analysis. The data remains, permanently archived in digital repositories that preserve humanity's most detailed portrait of the early universe for future generations, who may find new patterns hidden within the ancient light. The background radiation continues its eternal journey through expanding space, carrying the memory of quantum fluctuations that seeded all subsequent cosmic structure while fading gradually toward temperatures that approach absolute zero. In the universe's far future, when the last stars have exhausted their nuclear fuel and consciousness has flickered out across the cosmos, These photons will persist as the final electromagnetic testimony to the brief epoch when space first became transparent and light began its endless voyage through the growing darkness between worlds. The cosmos sleeps,